All right, so yeah, welcome back everyone to the third day. Just wanted to ask about the coding exercises. So, as you know, yesterday I posted a link to the coding exercises. There was the first very small exercise for things that we discussed yesterday, and there's more exercises for today and tomorrow, and it's all on that one page. And remember that you can use Slack for peer support, discuss with each other if you have questions or if want to see what the other guys are doing. But also, if you find any problems with the actual files, like bugs or something like that, then you can go up on GitHub and you can submit an issue here, and then Lucas, who's one of my PhD students, he will then clear it up. So I wanted to ask, hands up if you're actually already working on the exercise. Who's actually trying it around? Okay, a few people already. Yeah, good, nice. All right, so everyone else, please look into it as well. It's, I think, very helpful for you to actually internalize some of these ideas. So that's about the coding exercise. Um, Then I think it's nice to go back to this again, just a quick warm up. I want to hear from more people. Why do you care about MARL? Why do you want to learn about MARL? What do you want to do with it? And I want to hear from more people. It's also interesting for me to see what kinds of applications you have in mind. So I'm going to first want to see if there's any hands up volunteers. If not, I'm going to pick some volunteers. Who wants to share? Don't be shy. Okay, I'm going to pick some people, volunteers. How about you? You there? Yes. And I think we have microphones there. Why do you want to learn about MARL? What will you use this for?
So I have an application, a scenario where a robot has to perform a task, but it has to consider multiple users' preferences. And these preferences can be different or conflicting. So one of the possible approaches that we thought to tackle this problem is to model the users as agents and make them do the discussions.
Do you have them do discussions? Okay, interesting. So they're agents and they exchange information, and then what's the goal for them to agree on some outcome?
Yeah.
Oh, okay, interesting. Yeah. Okay, nice. Yeah. Who else wants to share? Okay, volunteering algorithm. You there, pink shirt.
Well, actually, my research is in explainability. So I think that, but not applied in reinforcement learning or deep learning, more applied in optimization. But I actually think that maybe trying to apply explainability in reinforcement learning, it would be very nice in the future.
Okay. Yeah, there's interesting work already in explainable multi-agent reinforcement learning. There's a Israeli researcher, Sarit Kraus. She was actually my on my examination panel for my PhD, and she has done a few papers now with her group where they're trying to develop multi-agent RL, but in a way where I guess we can understand why they're making certain choices. So yesterday or 2 days ago, I showed you some videos of some, warehousing tasks, right? And some crazy things are happening. And for us, when we look at this, we talked about this yesterday, it's hard to understand the logic, like why are they doing certain things? And these things are not designed to tell us why they are doing this, right? The logic is not clear. And I think the idea there is they want to explain, like they want to have systems that actually provide this kind of logic, why they're doing certain things. And that's interesting, right? It's important. Okay, here from one more. How about you? Yes.
I'm also working on an explainability method whose name is policy graphs, which my colleagues have tested on single agent and multi-agent scenarios like cart poll or overcooking, and now I'm testing it on driving scenarios.
Okay.
So it has something to do with MARL. That's why I wanted to explore more.
Yeah,
and also,
nice. What driving simulator are you using?
No, I'm using New Scenes now. It's a data set of
Yes.
real-world driving scenario, but it has many limitations. It's for my master thesis, so when I will finish, I will explore other data sets.
New Scenes is one of many. New Scenes is just a highway driving, right, in the US.
US and Singapore also.
Okay.
Also has urban scenarios,
Okay.
but very simple scenes, like never happens that an ambulance comes and.
Yeah, interesting. We actually, I told you we did this business for self-driving, right? And we had a whole lot of research in that area. And I can actually point you to some papers we've done with really interesting, what I think is really interesting multi-agent research. But what we haven't actually done is to apply multi-agent reinforcement learning in self-driving, because we actually really just control a single agent that is acting in a multi-agent environment. So we do not actually control the other guys, right? So I think multi-agent RL could still be interesting there to train other policies to make your guy more robust, basically. But most of the work we do in self-driving is more classical optimal control, theoretical approaches, and also inference and prediction and goal recognition and that sort of thing. Maybe you find this helpful, so I can point you to some papers. Very good. All right, thank you. Okay, good. That was just a little nice warm-up again. And the last thing I want to say before we move into today's lectures, I was thinking for today it would be kind of nice to grab lunch together if you want to stick around. So I think there's a canteen, which is maybe a 5-minute walk from here, directly there. And if you want to stick around, I'm going to be there. We can all go grab lunch together. But everyone pay for themselves. I'm not paying for everyone, okay? So maybe after the lecture, we can just hang out and meet at the door, and then we can go together. Everyone welcome. All right, good. Then let's get into today's lecture. So today we'll be talking about deep reinforcement learning. And of course, deep reinforcement learning is a really hot area. There's a huge amount of research going on in deep reinforcement learning. And as I told you, my entire research group, for example, is about 20 people. Everyone is hardcore focused on developing reinforcement learning algorithms, including multi-agent reinforcement learning. There's many other labs as well that they're trying to push this. And some really big results have come out in the recent years where they did some incredible results and incredible new applications. And the reason why we're actually talking about single agent reinforcement learning, this is all just about single agent reinforcement learning, is because we need to know all this stuff before we move into the multi-agent setting. Because a lot of the multi-agent reinforcement learning algorithms, they are in one way or another based on the single agent ideas. They are either extending them or they sort of use similar ideas and philosophies. And that's why I think it's very important that you know about the single agent RL ideas as well. And that's why the book is structured in this particular way as well, right? So first we start with the single agent RL in part 1, and then we do the multi-agent stuff. In part 2, also, we first start with deep learning and then single agent deep RL, and then we do the multi-agent thing. So it's very important that you spend your time on the single agent setting as well to understand what's going on. So I was thinking, we're going to spend some time to go through some of these very basic ideas, and some of these things you get to try out as well in the code base. And I wanted to just ask again, who here is actually already familiar with just basic deep learning? For example, implementing deep learning-based machine learning in Python. So hands up if you already have some experience. Okay, hands up if you actually have done deep single-agent reinforcement learning. Okay, some hands here, that's good. But I think there's more people who actually haven't done that yet. And so we should spend some time on this. This is working, yes. Okay, this is the book again. Want to make sure you all definitely know about the book, so you go ahead and buy this after the course. You can already get this on Amazon, and someone decided this cost $65. It was not me, but anyway, it doesn't matter. So you can get the book. All right, so here's the lecture outline. We have deep Q learning. This is probably the most basic, most foundational deep reinforcement learning algorithm that is around. And in fact, this started in 2013 when the guys that then became DeepMind first released this piece of work where they did deep reinforcement learning for Atari games. And still to this day, it's an important baseline algorithm, and a lot of work is based on this approach. We're going to talk about some problems with this basic approach, moving target problem, and correlations in consecutive experiences. This was for a long time a problem when people tried to use neural network representations in reinforcement learning. They could just not make it work in a stable way. And one of the big contributions with this deep Q learning approach is that for the first time, they introduced some very basic approaches that actually dealt with this moving target and the correlation problem. And then for the first time, they were able to train neural network-based Q functions in a stable way. And then after that, we'll talk about a different class of algorithms, which is called policy gradient algorithms. The difference is that in deep Q learning, as the name suggests, we're still doing Q learning, which means that we learn value functions. We learn to attach values to actions, and then we create policies that use these Q functions. But in contrast to that, you can also have algorithms that directly parameterize a policy. So there's no Q functions. In the purest sense, there could be no Q functions, no value functions. And then there's just a neural network that represents your whole policy. And now I'm actually optimizing the parameters directly in the neural network without any value-based proxy models. And of course, there's also methods in between. For example, actor-critic algorithms, which are probably the most important class of deep reinforcement learning algorithm. They're actually doing both. They maintain value estimates and they also do policy gradients to optimize parameters and policies. Okay, and then lastly, we got to talk about concurrent training approaches, which are very important if you want to make this practical and scale it on bigger machines. Okay, so this is a little bit more material here, but none of this stuff is too complicated, I should say. Conceptually, all of this is pretty straightforward. So bear with me, and if you have any questions, anything not clear, just interrupt me and raise your hand. If you feel I'm not seeing your hand, feel free to say, hey, I have a question. Okay, so don't be shy. Okay, deep Q learning. Right, so deep Q learning, that's just what we call it here. Actually, the name that people use is DQN, which stands for Deep Q Networks, to emphasize the idea that there's now a neural network that we use to represent this. But actually, deep Q learning might have been maybe a more intuitive name. Anyway, the idea now is that we use a neural network to represent the Q function. You already know about the Q function. You learned about this on the first day. And now we're doing the same thing, Q functions, to estimate values, expected returns for different actions. So first, this is the neural network, right? So you know what this looks like. As the input in the input layer, there's going to be, for example, the complete state description in a Markov decision process. You assume that you have access to the state. Then there will be a number of layers in between. There's lots of different things you can do there. If you know about deep learning, you know there's lots of different types and techniques. And then in the output layer, there will be the value estimates for the different actions you can take. So in a particular state, which we gave as input, we will give values for the different actions. And typically, this network would be designed to actually output an entire vector, not just an individual action value, but actually the action values for all possible actions you can take. And at the end here, this is the theta is the set of parameters that define the neural network. Not sure what's going on here. Maybe I need to fix that in the slide. Let me make a note. By the way, every day when I find 2 or 3 of these typos, I fix them. So the ones from yesterday already have been fixed, and you can download the new slides again. Slide 3. And as I always say, if you find any other typos, please do let me know. Okay, slide 3, fix that. Yeah. Yeah, it could be a square loss. Yes, that's simply what we do. But I think in this case, Lucas decided to remove that for simplicity. But I agree. I think I should probably add this square here as well. Mean squared error. Okay. Yeah. Thank you. Anyway, the important thing is here we have this network description. And there's an input, which is a state. And then as the output, we give the values for the different actions. And you need to train this model, right? If you have a neural network representation, you want to train the parameters so that the input is mapped into a particular output that you care about. And here, the output that we care about is actually the action values. The point of this is to say, well, we need to have a loss function. That's where the L is coming from. There's a loss function, and we need to minimize this. And we can take differentiable loss functions. We can then compute gradients, and then we can use those gradients to optimize the parameters. That's basically the story here. But the loss function describes basically how we want to shape the output to be as close as possible to some sort of quantity that we care about. In this case, we care about the actual true. We care about a label here, white t, which is supposed to be the actual values for the actions that we're estimating. And so we're saying that the difference between our actual estimate from the model with the particular parameters and the label that we care about, which is the true values, should be as small as possible. Okay, that's basically, I think that's why he didn't have the square in here, because the message is clear already without the square. The square just ensures that it's positive. Okay, but unlike supervised learning, we are not given this Y label beforehand because it's not supervised learning. Hands up if you know what supervised learning is. Yeah, almost everyone. Okay, so then you also know why this is not supervised learning, because in reinforcement learning, there is no label. The labels would be the actual values or the actual actions that you should be taking, but that's not provided. The only thing we have that we can work with in reinforcement learning is the proxy reward signals, which give us an indirect measure of goodness, but we don't actually want to maximize the rewards. We want to maximize the return, right? So this is something else. So we only have this indirect reward label. What we can do though is we can use a temporal difference learning update, just as we did in Q-learning. So now let's say we define this label YT as follows. Either it's just the reward at time t if the state, the next state is a terminal state, and that makes sense because there's nothing to bootstrap. We now finished, so it should just be the reward at that point that we received. But if it's not a terminal state, the successor state, then we need to do the bootstrapped temporal difference update, which is the reward plus one application of the discount factor times the maximum action in the current estimates in the Q function. Okay, so we take the maximizer in the current Q function parameterized by theta. And that's exactly the same as what we did previously for the TD learning and Q learning. Okay, I think that should look very familiar for you. And basically, if we define our labels like this, then that defines our loss function that we use to train this neural network. Now we just have to collect these different data points, right? We have to try and we see the outcomes of actions and the successor states and the rewards, just as we did with Q-learning. Okay, so here's what we call naive deep Q-learning. It's naive because it actually doesn't address a couple of important problems that you need to address to make it stable. But it's still interesting to look at this just as the most basic version, basically. And then we talk about why this is not actually enough. Okay, so let's look at this. First, we initialized a value network Q with random parameters. You can actually initialize in all kinds of ways, but let's just say you have a random parameter vector. And for those of you who are familiar with deep learning, the parameters would be basically the weights and the coefficients that define the nodes inside your neural network or the units. Okay, so then we go through your episodes, and every episode has a number of time steps, starting with T0 and going on. You at every time step, you observe your current state. Then you do your epsilon greedy action selection as before. So either with probability epsilon, you choose a uniform random action. That's your exploration. Or otherwise, you choose the current greedy action, which is the one that maximizes the current Q function estimates with the current set of parameters. Then we apply the action, we observe a reward, and then we observe a successor state at the next time step. And then we do our update. If the successor time step is a terminal time step, then we just take as the target the reward that we got. That's what you just saw in the definition for the Y label. And if it's not terminal, then we do the temporal difference bootstrapped target, which uses the current reward and bootstraps from the value of the successor state using the maximizer. So that defines our label Y. And then we apply define our loss, which is basically just the difference between the current estimate and the label that we just computed, the target. We want that to be as close as possible. So you see here's the square that you just mentioned there. That's actually when you want to make it, when you make it differentiable and then you execute it in your parameter updates. And basically, you then do a little bit of gradient computation and something called backpropagation. That's something that it's not actually covered here, would be covered in the previous chapter. But basically, backpropagation is the most important algorithm in deep learning. It allows you to compute gradients. And you use this to update your parameters theta by minimizing this loss, for example, one step. Was there a question here somewhere? So hands up or something. No? Okay. So that's the most basic naive deep Q learning. But it's called naive for a reason. It's actually not addressing certain complications. And we're going to look at this next. So this naive application of neural networks to RL algorithms has some problems. What are these problems? First problem is what we here call the moving target problem. And so the issue is that we have these bootstrap targets, right? So we're updating an estimate by using other estimates from other places. In this case, we're using the estimate for the successor state, ST. And that's defined by the current parameters that we have. But one issue is that with neural networks, the reason why we care about neural networks is because they're supposed to generalize the inputs. So if you have billions of states and you have certain inputs, you will never be able to observe all of these billions of states in your whole lifetime, right? You will not be able to explore the full state space. You will be able to explore maybe 1, 2, 3% of the state space. But you want your neural network to understand concepts and to generalize inputs to outputs, even inputs that you've never seen before when you reach them for the first time. That's the whole reason why we do deep learning, to understand features and extract useful, meaningful features or representations. So that means that if we do one update in one place for one particular state, it can actually change the outputs for all kinds of input states, not just for that one particular state that we're just updating. And it means that this Q function can change quite a bit, especially in the early days when we train it. So now there's this idea that this Q function becomes non-stationary in all kinds of input states. If we make updates in state 1, it could also change the value estimates for states 2, 3, 4, and 5. But we haven't updated those yet. And so it means that this Q function becomes a moving target that we're trying to track with basically over time. The targets Y depend on theta, and any update to theta changes the target basically. This non-stationarity of the targets makes it difficult to learn the optimal parameters for the neural network. And so this is not addressed in this naive implementation of Q learning. It's a problem. This was for a long time a problem that people faced when they tried to use neural networks to represent Q functions. How can we address this? Well, there's actually a few ways to address this, but the one that they proposed in this 2013 work and subsequently in 2015 when they published this in Nature is to use what's called a target network. Okay, so it's a really simple idea. There's now a new network, a second network basically, and that has also a set of parameters, which we call a theta hat here, or theta bar. And we're saying that this target network is updated less often than the actual network that represents the Q function. So there's two networks. They're nominally supposed to learn the same thing, which is the Q function, but one of them is updated less often than the other. And by doing this, by having a target network that's updated less often, it means that it's easier to track. It's not moving so quickly. It's not moving very erratically. It's much easier to track because it's not moving places so quickly. And basically, the idea now is that we can actually use the target network and use that in the value bootstrap here. And that means when we bootstrap now, basically the target network is it's more stable as a target. So it's called target network because we use it in the temporal difference target. That's where that name comes from. Okay. There's a second issue, which is that these samples that we get to observe from deep reinforcement learning or in reinforcement learning, they are correlated temporally, right? So here's an example. This is actually an environment that you can play with from a particular suite of games you can basically try in reinforcement learning. And you have to sort of control this spaceship and do various actuations to, basically travel and land, I think, between the two flags, basically. And it's kind of complicated. There's certain dynamics going on and, you can't fully control it. So you have to do some smart controls. But if you look at this, the sequence, what it's supposed to show is that, one frame is very closely correlated with another frame. For example, the immediate frame would just be a small difference, and then the immediate next frame would just be a small difference again. And you see how there's this correlation going on, right? So these subsequent frames, they're closely correlated with one another. And that means that actually this basic assumption in neural networks, which is that you have independent and identically distributed data points, is not satisfied here. They're heavily correlated, and the distributions change over time. In the different states. So this is a problem. This correlated data can lead to overfitting in the value function. This is one of the other big problems that people experienced in the past. And in particular leads to overfitting to the more recent experiences. Okay, so let's say we're having a long sequence of frames that we get to observe over seconds, and we always do the updates based on the most recent frames that we just saw. And what it means from a deep learning perspective is that we place heavier weight on the more recent experiences because they were the most recent updates, and any update can change anything in the neural network, basically. So that can lead to overfitting to the more recent experiences that we collected. And in return, it leads to something that could be called catastrophic forgetting. So the new stuff we care more about, recency bias, we overfit more closer to the recent things, and we begin to forget the old things that we used to learn, that we optimized previously, maybe, many time steps ago. And we don't want that. We don't want to forget the things we did and many time steps ago, because we need to know all of these things, right? We want the network to remember all the important pieces of information. So these are two problems we need to address: the moving target due to a quickly moving Q function that we use in the bootstrapping, and the correlation of successive or consecutive samples. The solution here for the consecutive experiences is that we actually collect experiences in a replay buffer. This is a term that you see many times in reinforcement learning and deep reinforcement learning. It's used still today in the most recent state-of-the-art deep reinforcement learning algorithms, especially a class of algorithms called off-policy algorithms, which I think I already mentioned yesterday. Q-learning is an off-policy algorithm because it's in the target, it's actually using estimates for data that it's basically never experienced itself by using a nonlinear max operator. So we have a replay buffer where we basically collect all the past experiences, and then when we collect our data on computer gradient to update the parameters in the network, we actually randomly sample from this replay buffer. So we have some experiences from there, some experiences from here, from there, from different points in time. It means we're breaking through these consecutive correlations. We're breaking through time, basically. We're breaking through these time slices. And by doing that, we basically help the network to remember things that happened across time. And we avoid the overfitting to the more recent experiences. So in summary, DQ networks, or DQN, is a foundational deep reinforcement learning algorithm. And we have a neural network that represents the value function, the action value function. We also have another value function that's supposed to be doing the same thing, but it's moving more slowly. This is the target network, which we use in the bootstrapped update targets. And then we have this replay buffer, which is supposed to store experiences, and then we randomly sample from the replay buffer to do the training. Okay, so in a little bit more detail, looks like this. We use our target network, which has the parameters theta, but with a bar above. And basically, the targets now look like this, the temporal difference update targets. There's the reward again here. There's our maximizer over the Q function for the successor state. Oh, I think there's another typo here. This should be up in the superscript. But we're actually using not the parameters theta from the actual neural network. We're using the parameters from the target network, theta bar. Let me make a note here. Okay, so I think that's basically straightforward, right? It's the only thing that we've changed now is which parameters we actually put in here when we compute the target. But when we select actions, we still use the actual main value network that we train, which is with the original parameters theta. So that's when we do our epsilon greedy action selection. We update the parameters of the main network theta by minimizing this loss that you saw earlier. And we also update the target network, but in less frequent intervals. And there's a few different things you can do. You can directly copy and paste the parameters from the main network to the target network. That's called a hard update. That's just like complete copy and paste, hard update. Or do we have this in slide here? No. Another approach is what's called soft update. So you have some interpolation with some hyperparameter that is so supposed to just do a little bit of moving from the main parameters to the target parameters. So both of these ideas are designed to just make sure that the target network moves more slowly. When we do the hard copy, then we do this hard copy in at a much lower frequency than when we actually update the main network. If we do the soft updates, which is when we have a parameter to interpolate, then we can do it at the original frequency, but by doing just a smaller coefficient, it will still be much smaller in terms of how it changes. Okay, and then the replay buffers, and again, a little bit more detail. We have these experiences that we collect over time when we explore, states and actions that we try and rewards we get and successor states we get to see. One of these things is called an experience, right, or a data point. And we collect this over time in our replay buffer. The replay buffer is just that, just a buffer that stores experiences. To compute the loss, we sample batches of experiences from this buffer. Typically, you would just do a uniform at random, but there's actually much smarter things you can do as well to have more efficient learning. For example, there's something called prioritized experience replay buffers, which is when you use some kind of smart techniques to weight the importance of the experiences, and then you turn that into a probability distribution, and you sample based on that distribution. But the easiest thing you can do is just a uniform random distribution, and you sample a subset based on that distribution. Okay, we're taking some pieces from this replay buffer, uniform randomly, and basically by doing that, we're breaking through these time correlations. Random sampling breaks through the correlations, and it reuses experiences that we had in the past. So it means that we are not forgetting things. Improved sample efficiency. This is something I just mentioned earlier. Replay buffers only work for off-policy algorithms, which is reinforcement learning algorithms that are designed to actually use data that do not come from the actual policy that we're training. And that's what Q-learning is, for example. SARSA, which is this first algorithm that I showed you on Monday, is an on-policy algorithm, which would not be able to use off these replay buffers. So here's now the full pseudocode for the actual DQN algorithm that was used in the Atari games and that a lot of people still use as a very basic baseline. And this includes these two modifications with the target networks and the replay buffer. So let's go through this just a little bit. We initialize the value network for the Q function with random parameters. We initialize the target network with the same set of parameters. And then we initialize an empty replay buffer. And then we go through our episodes and time steps. We observe the state. We do our action selection as we did before. We apply the action. We get a reward and see a successor state. We store this collected experience in our replay buffer. This is now a new line. And then there's also a new line. We now randomly sample a set of experiences from this replay buffer. This is also sometimes called a mini batch. You often hear this term in reinforcement learning. A mini batch just means it's a subset from the replay buffer. Then we do our target label computation if the successor state is you then do this for all the experiences that you sample in your mini batch. If your target is a successor state, you just use the reward and not bootstrapping. If it's not a terminal state. And if it's not a terminal state, then you do the bootstrapped target here. And keep in mind that you're using the parameters of the target network. So that's why there's theta with the bar above here. And then once we have done this for all the experiences that we had in our mini batch, we then compute the average loss. That's why you have the sum with the division here. This is just the average loss. And then we use backpropagation basically to update the parameters of the linear network by minimizing this loss here over the batch. Okay. And lastly, in a set interval, which could be every 100 or 1,000 time steps or whatever you want to do, you update the target network by copying over the parameters from the actual value network. This is the hard copy that I mentioned earlier. And this pseudocode is now complete. That's what they use in the Atari game, and it works really well, really quite robustly still for even for today's research. And there's many more other advances you can throw in there to make it even better. Okay, now we're gonna let's see about time. Yeah, there's a few more interesting things you can do. For example, one problem with Q-learning, which is also inherited by deep Q-learning, is the idea that these algorithms tend to overestimate. They optimistically tend to overestimate. And I guess the explanation is already here, but I want to see if people can guess why this is. If you only look at this here, don't look at the explanations down there because it kind of gives it away already, but only look at the line here. What do you think is meant by that, this overestimation bias? Why does this happen in Q-learning? Don't read this. Just think about it yourself. It's an interesting experience, an interesting exercise. Anyone? Yes. Okay, I can just repeat it. Yeah, but basically, you were too fast for the microphone. Too fast. But basically, the idea is because we have this max operator, and because we have our estimates, which can be all over the place initially, right? That can be really wrong and give all kinds of weird estimates initially. But because we're backpropagating the max in any point in time here when we apply this, it means that even if there's a false maximizer that should not be maximum at all, we still backpropagate that initially. And that means in the early phases of learning, there's this bias that we tend to use the max estimate, the maximum estimates early on, and they get backpropagated to all kinds of other states. And it can take a long time sometimes for this to clean up, so to speak, collect enough experiences so that you lower this over time. You understand what the actual values are. So this overestimation bias can be a problem for learning. it can take a long time to actually fix this during learning, basically. And I guess that's explained here as well. So using the max operator, select the maximum value estimate for the target. That's what we're doing here. Oops. Since our value estimates do not necessarily reflect the true value function, that's when we begin the learning and it can be all over the place. The max operation will likely select overestimated action values. And that can slow down convergence because that's propagated back to the other states. So what's the solution? Or let's say that it's a approach, a solution is not the only one. It's this idea of double Q learning. And like that's also still, I think, fairly broadly widely used. And even if it's not used in your particular algorithm that you're trying, I think it's important to be aware of this because it's conceptually an issue with using a max operator. So the double Q learning reduces the overestimation by decoupling the action selection from the value estimation using separate function approximations. So it's kind of similar to this idea of a target network where we have separate networks that represent the same thing. And they used one is used for the action selection and one is used for computing the targets. And something like that we're doing here as well. Let's see how this works. So we can do this with minimal changes of DQN. DQN, which is double DQN, uses the primary key network with the parameters theta to select actions. This is what we've done so far. While using the target network with the parameters theta bar to estimate the action values. And so now the difference looks like this. Again, as before in the label, as if the successor state is a terminal state, then we just use the reward. But if it's not a terminal state, then you can see that we do basically an update like this, where we're moving inside here, the maximum action that we're using to evaluate the bootstrapped target actually comes from the true value network, which is with the parameters theta. But then in the bootstrapping, we're actually feeding this action into the Q function that uses the parameters from the target network. So you can see the difference is that here, previously the argmax used to be outside here, and then we maximize directly over the actions in the target network. Now we're actually doing this argmax inside here by including another Q function inside that uses the original parameters. So it looks a little bit complicated, but it's actually not complicated at all. And the implementation is very straightforward as well. And because we already have the target network anyway, you might as well just do this. It's not like you have to learn anything new. You have this already. You can just use this now in the max operator. And by doing this, basically it addresses this overestimation bias because we now have two different functions from which we actually take the max. And they basically makes it more robust because now if these estimates tend to change over time, we take them from the original Q function. So let's see how deep Q learning works in practice. We have the level-based foraging task. And in this case, it's very simple. It's just single agent here, and there's just one apple here. There's no levels shown here because we just keep it simple. The one agent can collect that one apple. And here on the right, you see some results with different reinforcement learning algorithms. So this is all DQN or deep Q learning. The blue one is the naive one, the one that we called naive at the very beginning. It doesn't do any of these special tricks. Then there's the one that you only uses the target networks. Then there's the one that only uses the replay buffer. And then there's the full thing, DQN, which uses target networks and the replay buffer. And the learning curves look like this. On the x-axis, you have your training time. And on the y-axis, you have your return. So you want to be as high as possible. And you can see that all of these lines are pretty slow to learn, especially if you look at the blue line, which is the naive one. And then the one that works really well is the full DQN algorithm that uses both of these tricks, which is the target networks and also the replay buffer. So you can see that if you remove any one of these things, the replay buffer or the target network, you don't get the performance that you want. It's all performing not so well here. You need both of these techniques to make the training stable, and then you really get good performance here. So I think this plot nicely shows the contribution of the individual things that we added here and why they're both important in combination. You cannot learn without them. Okay, that's what it says here. In isolation, neither the addition of target networks or replay buffer are sufficient to learn in a stable way. Okay, so that was deep Q learning or deep Q networks, which uses these replay buffers and the target networks. Before we get to the next class of algorithms, which is policy gradient algorithms, just want to see if there's any questions about the deep Q network algorithm. Was this clear for people? Makes sense? Straightforward? Okay, good. Then I think let's go into the next type, which is policy gradient algorithms. So I mentioned earlier, there's this other idea, which is that we don't actually have to maintain explicit value estimates. We can directly change the parameters of a neural network that represents your policy directly. So that's what's explained here. We previously, so far, we've considered a parameterized value function. That's what we did in deep Q learning or deep Q networks. But we can also directly parameterize the policy that we're learning, and then we change those parameters directly. So now we use a neural network, and then it's for a neural network for a policy pi with parameters phi. So this we just use phi for policy parameters and theta for value function parameters. The policy network receives this data as input. You know this already, like in MDPs, and outputs a scalar value for each action. So kind of similar to what we did with the Q function, where we outputted a vector of action estimates. But actually here now the policy outputs a distribution over actions directly. And in the neural network, that means that we have a vector of scalar outputs corresponding to the actions that we can pick. These scalars, let's say we call them L for state action, state and a particular action. There will be these scalars. They represent, let's just call them preferences of the policy to select a particular action A in a state S. Okay, we use this vague term preferences because that's not the end of the story. This actually needs to be mapped into a probability distribution still. And the preferences are used to actually map it into a probability distributions. So these preferences are then transformed into a probability distribution across the action space that we can pick. In this case, using a softmax function. Softmax is a very common function that is used in not just in reinforcement learning, but in deep learning altogether, because it basically looks like this. And this is an expression that you can very easily differentiate, which you need to compute gradients to update the parameters of the network. So the policy pi is now defined as follows. It gives you the probabilities for a given action if you're in a particular state, and with the network parameters phi is defined as this, an exponential of the preference function for that particular action in that state. And then you divide by a denominator which sums over all the possible actions and taking the exponential preference. So it's a way to normalize your preferences. By doing this normalization, you turn these values into numbers that are between 0 and 1, and the sum of them will be 1. So it's a probability distribution. And that's what the softmax does. And because we use exponentials here, and they're only elementary computations where product and sums and division, it means we can actually easily compute the gradients for the softmax representation. Is this clear for people? So we have a network. It takes as input the state, does some internal network computations. On the output, we give these preferences for the different actions, and then we use the softmax definition to turn these preferences into actual probabilities, which means that preferences that used to be, any kinds of scalars, they're now actually defined to be between 0 and 1 and probability distribution. They're normalized. So let's look at some interesting graphs that show some properties. Why do we actually want to do this? To learn directly a policy rather than a value function? Well, it turns out that if you learn a value function, then you're pretty limited in terms of the flexibility of the kinds of distributions you can represent in your policy. And that's due to the nature of how epsilon greedy policies work. So here's an example. Let me explain what this actually shows you. Let's say we're in an example where there's 3 actions, A1, 2, and 3. And on the y-axis, you have your probability given by a policy for each of the 3 different actions. And so there's a few different bars we're showing here. First, let's only look at the blue bar. The blue bar is a fully greedy policy. In this example, let's say the greedy action is action 1. This one has the highest Q value. It means that all the probability goes to this action and all the other actions get 0 probability. That's why there's not a blue bar. Okay, what can we do now? Well, the next thing we can do is epsilon greedy, which is when we, for example, have epsilon 0.1. Then we give 0.9, more than 0.9, but basically less than 1 to action 1. And we give a little bit more probability to these other 2 actions. We can have a higher epsilon 0.5. It means now that the greedy action gets even less probability and the other actions are sampled more often. So you see how the story goes. And then if we take the maximum value for epsilon, which is 1, then we have a uniform random distribution. Okay, completely randomized. So that's all we can do with value functions. And if we use epsilon greedy, that's as far as we are able to represent probability distributions, but it's very inflexible. It turns out that in some applications, you actually need to have much more interestingly shaped distributions in order to reach optimality. So nothing that looks like this, but maybe bimodal distributions, or maybe things that where there's more interesting distributions of your probability masses. In contrast to that, with your probabilistic policies that can have any kinds of outputs, you can represent any kinds of probability distributions. So again, here we have the three actions, and on the y-axis your distribution. And in this case, we can arbitrarily represent all kinds of distributions. They have all kinds of shapes. And it could well be the case that in a particular situation, you need a shape that looks more like this one here, or more like this one. And neither of those you would be able to represent, or like the green one, for example, you would not be able to represent with epsilon greedy policies. So that's why we care about learning direct policies. Another benefit is that they're also very helpful when you have continuous action spaces, which is often the case in robotic control problems. And if you have continuous action spaces, then you cannot represent Q functions as we've done before. Okay, so moving forward, now we need a way to actually optimize directly these parameters in the neural network that represent your policy. And for that, we have something called the policy gradient theorem. That's probably one of the most important results in all of reinforcement learning. This was developed in the early days by people like Rich Sutton and others. And basically, this was it's the foundation for a whole family of policy gradient algorithms, which instantiate this policy gradient in all kinds of different ways, including recent state-of-the-art algorithms that are still traced back to this foundational result. And they just basically do various instantiations of that basic result. So the question is, how do we update the parameters phi of the policy? Okay, we need to update directly these parameters. There's not those y levels anymore that we had before, where we had the difference between the targets and the estimated Q functions. Using the policy gradient theorem, we can express the gradient of the performance of a policy with respect to the parameter phi of the policy. And it looks like this. This is actually already taking the gradient of a particular loss for the policy parameters, and that's proportional to what you see here. It's very straightforward. It basically means for you sum over the states, you have your state visitation distribution. It's mentioned down here. Basically, it's the frequency of visiting the different states times summing over all the actions you have available, and then for each action you take the estimate in your Q function. And you multiply this by the gradient of the policy with respect to the current policy parameters of that particular action in that particular state. So it's a straightforward piece of theory here. J is the function that measures the quality of the policy. So we want to maximize this, which means that we need to take a gradient. And that's basically what we then use to optimize the parameters. PR is the state visitation distribution, just mentioned that. So it's basically gives a number of between 0 and 1 for each state, according to the current policy. And Q is the value for a given action under and the state under pi. In practice, we don't know this. This is a theoretical construct. In practice, we need to estimate this, so we can take sample estimates or value functions and so on. And the Q function is basically our new loss function, the J function. Previously, we had the J function defined as the difference, the squared difference between the label Y and the Q value, and now it's this basically after we take the gradient. And the difference is now that we don't minimize the loss, we actually want to maximize this. This is describing basically the performance or the goodness of the policy. But maximizing and minimizing is the same. One can be mapped into the other. It's just a difference in signage. Okay, so one more thing on policy gradient theorem assumes that this state visitation frequency is actually given under the current optimized policy pi. So it means that we actually need on-policy data. On-policy, remember I mentioned earlier this off-policy idea. Off-policy means that you have an algorithm that uses data that does not come from its actual policy, like Q-learning. On-policy is like SARSA, when all the data used for learning actually came from the policy that you're just optimizing. And that's just a requirement of the fact that we have the state visitation frequency here. Okay, so if we continue this, now we need to do something with this. This is still just a theoretical construct that we cannot actually execute in practice because there's things that we don't know, and also there might be far too many states and too many actions. Oh, by the way, there's this derivation here. I think I'm going to skip over this here. And instead, yes, so let's look at this here. This is more interesting. So now if we look at the policy gradient, this is just after a few derivation steps, it looks like this. We need to interpret these three components that we have in our policy gradient. And basically that's what we're doing here. So first, let's look at this here. The gradient of the policy in a particular state for a particular action that basically points into the direction of that most increases the probability of taking that particular action in that particular state. So that's our first gradient, the raw gradient. That action in that state, the gradient points in the direction to most maximize the probability of taking that action. That's one part of the policy gradient. But now we have a modulator or regularizer, which is in front. This is the Q value for that action in that state. And that basically represents the goodness of that action. So it's like a measure of quality. If the Q value is very high, then we really want to emphasize this gradient here. We really want to increase the frequency of doing that action. But if the Q value is low, then we want to not emphasize repeating that action. And lastly, there's an inverse factor here, which is a normalization coefficient by dividing through the probability of taking that action. And that is because the training data might actually skew your updates. Basically, if you very frequently observe this action A, then you want to take the inverse of that to account for the frequency there. Otherwise, there would be a bias to actually increase the frequency of that action when it shouldn't be increased. So these three main components define the policy gradient. And I think they're actually they have a nice meaning attached. Each one of these three elements has a nice role to play in this bigger picture here, basically. And maybe when you get back home and you look back at the slide and in the book, you can take some time to really try and interpret the meaning of these three components and why they're all needed together. Okay, so now let's look actually at the first algorithm that we can instantiate from this piece of theory. And it's called reinforced. This is one of the first policy gradient algorithms that came out in the literature, I think from 1992 or so, the paper was. And it's still used in some very basic exercises. Usually when you learn about reinforcement learning and you learn about policy gradient algorithms, this would probably be the first algorithm that you would get to implement yourself because it's just so simple. Okay, so reinforce is a policy gradient algorithm that uses Monte Carlo or MC estimates to estimate the Q value for a particular action. So Monte Carlo, hands up if you know what that means. Maybe who has heard that before? Okay, Monte Carlo is just a weird name to describe sample-based. I don't know why it's called Monte Carlo, to be honest. Does anyone know why it's called Monte Carlo? Someone knows? Ah, okay. Casinos. Okay, nice. Yeah. But I think I prefer the term sampling based. We just I've put it up here because it's still a common term that a lot of people use. But Monte Carlo simply means sample based when there's stochastic effects or distributions. But basically, reinforce uses a sample return estimate, and it looks like this. So it minimizes a particular loss function for a given history. Let's say this is a history from one episode, the states and actions and rewards, all the way up to the current state. Here's our loss function for a given set of parameters, phi for the policy function. And we're basically going through these different experiences. Okay, so first, inside here, this is the return calculation for that particular episode. We're going to go through all the rewards, and we are just applying the discounting coefficient, and we're summing that up over time. Actually, I think this reward function could just replace with the reward here. Not sure why that wasn't done. Let me make a note. Okay. Yeah, because the reward is deterministic, I guess you can have the reward function and then you could remove the rewards from the episode here. But since we have the rewards here already anyway, we might as well just plug that in here. And then it looks a bit simpler. But it's the same thing. So this is the sample return. This is the Monte Carlo estimate. Okay, it's a sample return because this is actually from that sampled episode. It's not an expectation, not an average. And then Yes, and then on the far end here we have our logarithm over the policy. This is just a consequence of the policy gradient, and it has a negative sign because we want to maximize the expected returns. So that's what I mentioned earlier with mapping maximize to minimize. But basically, that's the whole idea. If you go back one slide back, or is it on the next slide? No, it's on the slide back. Just want to explain where this is coming in. So you see that we have this part here. This is the Q function that gives us this measure of goodness for a particular action in a particular state. But we don't know this in real. We need to estimate this somehow. And reinforce estimates this in the simplest possible way, which is the actual sample return that we experience at that point in time. Okay? So this thing here gets basically replaced with this thing here, the sample return. Okay? That's basically how you can think about this. This is a way to instantiate the policy gradient. But reinforce has problems. Because it's using a sample return, there's a lot of variance and noise that can happen. The returns can be all over the place if there's a lot of stochasticity in the environment. And so that's why reinforce is not really a state-of-the-art algorithm, but it's a very simple algorithm. It can learn very slowly due to the variance. So let's look at the pseudocode. It looks like this. First, we initialize our policy network with some parameters phi. These can be random parameters. Then we go through our episodes and the different time steps from T1 to all the way to T-1. We need to now have a final time step here because we want to compute the sample returns, which means they cannot be infinite. We have our state that we observe. We sample our action from our policy. One thing you will see here now is that there's no epsilon greedy. There's no value function, so there's nothing to greedify. There's just the policy that gives us the direct action probabilities, and we can sample from them. So whatever the current probabilities are, we're sampling from under the current parameters. We apply the action, we observe a reward, and we see the successor state. And then we do our loss calculation that we just saw for reinforce. So here's our sample return. You can see here actually we are using the rewards. And then we do back propagation, and we minimize the loss by updating the parameters. Okay. Yes. So this, as I just mentioned, has a problem, which is high variance. If you have sample returns, they can be all over the place because the environment can be very randomized. And the policy can be highly stochastic as well, which is when the probabilities are all over the place. When there's a lot of variance, that's typically bad for machine learning because a lot of variance is difficult to handle if you want to estimate the true averages, which is what we're trying to do here. So we need to address this somehow. And basically, one of the most basic but still effective ways to address this is called adding a baseline. It's just basically a function that gives you a mapping from a state into a scalar. And it turns out that the most common one that we can use is the actual state value function that we can maintain already anyway. So this can be learned using something like temporal difference learning, which is what we have here. And we can learn this value function and use that as a baseline. The baseline is just plugged in down here. So here is the sample return that we just saw. And now we're just subtracting from that this particular baseline. The baseline is just a function from the state. In this case, it's the actual state value. By doing that, you basically reduce the variance of by baselining against this state value, reduce the variance of the returns in the loss construction. And this is very simple to implement. It's just one line of code basically to add here. Baselines continued. It's important to understand that this does not actually change the gradients in expectation. And why is that the case? Let's look at a piece of mathematics. So here is our policy gradient that you saw earlier. Is proportional to this thing. And the only thing that I've done here now as a difference is actually subtracting the baseline, which I call B here. Otherwise, it's the same thing as what you saw earlier. We're just subtracting the baseline. Then in the next step here, we can pull out this part, the state visitation frequency, into the expectation, because that's just sampled from the policy. So we pull that out here. In the next step, we are actually just executing the product into the brackets here. And so that we have two expectations, one subtracted from the other. So you can see this times this, and this times that. And then in the next step, we know that this here can actually be spelled out directly by doing enumerations. So here, the expectation is turned into a sum over the possible states again, where we take the state visitation frequency times the baseline in that state, and we still have our gradient of the policy, or we can pull that gradient out if we go sum over the actions. And now the interesting thing is, this may be the most interesting thing in the derivation. On the left, it's still all the same. And on the right, this is still the same over the states. The baseline is the same as well, except here we now know that this is actually taking a gradient over a constant, because this sum here, needs to be 1. Pi is a probability distribution. If we sum over all inputs for pi, then we know it needs to sum up to 1. So it's always a constant. And you know that the derivative of a constant is 0. And so it means this whole thing disappears. And on expectation, we have recovered basically our original policy gradient again, sampled policy gradient. So this whole thing is just to say, adding the baseline does not actually affect the direction of the gradient, but it reduces the variance, which is important for us. Okay, now the next thing is actor-critic algorithms. And now gets a little bit more interesting. Actor-critic algorithms combine both of these ideas. You have a value function, and you have a parameterized policy. But I'm thinking maybe I should go back here. Before we talk about this, I just want to see if there were questions about the policy gradient algorithms. Because I guess it should be clear before we move to the next part. Was there any questions about that question there?
Do they still suffer from the not identically independently distributed data?
Does what suffer?
Does PG suffer, so policy gradient suffer from not having EED data? Because here we're not doing, we're not coping with it with the replay buffer. So how does this work?
We don't need to do that here because we have sample returns here, which already aggregate over time anyway. That's basically the reason why we don't need that here. And we cannot actually do replay buffers because the replay buffers, if we sample randomly from them, then they're not on policy anymore. But we need on policy because of this term here. This term is the state visitation frequency, which means this is only well-defined if the data only comes from that policy. But if you have a replay buffer, the data does not come from that policy anymore. And so this whole thing wouldn't hold. So in practice, maybe the more interesting thing is, which one is more efficient, policy, on policy or off policy, right? And in practice, it turns out that off policy is more efficient because it can reuse a lot of data that was previously experienced. We can resample that many, many times, right? In state-of-the-art algorithms, like PPO, for example, you rely on that a lot. On policy algorithms tend to be a bit more slow because they have to track basically these quantities that depend on the current policy as it's changing. I think I want to maybe take one more note for myself here. Yeah, I think this should actually be a different font style. Maybe you didn't see the lock here. Let me just make a note for myself. Okay. Good. So that's policy gradients. And now let's look at this actor-critic algorithms. And that's basically the last type of algorithm that we look at in this part of the lecture. And they're probably the most important ones, even for today's research, these actor-critic algorithms. So the policy gradient theorem allows us to optimize a parameterized policy, but we still need to approximate these expected returns. And in the reinforced algorithm, we've done this with these Monte Carlo estimates, which means we just take a sample return, but they have high variance. And they also require that you run an entire episode because you need to have an endpoint. And only after that endpoint can you actually sum the rewards to get the sample return, right? So that's also a problem with reinforced. It means that you cannot actually update on the way. You have to wait for the episode to finish. Actor-critic algorithms are different. So they aim to reduce the variance by using something like a baseline. And also they update more often. They don't have to wait until the end of the episode. They can do something like bootstrapping and temporal difference learning. So the interesting thing now is that we have two kinds of models. That's where the name comes from. We have a critic. This is the value function that we can learn to approximate. This would be plugged in here, for example, a state value function. And we have an actor. That's where the name actor-critic comes from. The actor is now the parameterized policy that we can directly modify. So we do both things now. We do something like in deep Q learning, which is when we learned the Q value estimates, and they are featured down here. We're replacing the sample return with the actual value estimate, and it maintains an actual parameterized policy as well, just as we've done in the policy gradient algorithms. And the critic is basically used as a training signal for updating the policy. By the way, if you wonder where the names come from, so actor is clear, I guess. It's the policy that's acting. And critic, it's called critic because it's critiquing the goodness of actions. Basically, that's why it's called critic, actor-critic, okay? One thing acts and one thing critiques the actions that we've just done, basically. That's where that name comes from. So if we look at this now, we have our expectation of the returns under a given policy. Remember that U is represents the return. And you can spell this out as this quantity here, which is the immediate reward, times plus a discounted return from the successor state, where the states and the actions come from that policy. And we know that if we maintain a value function estimate, we can replace that basically here with the V function here. So we now have these two things. We have a policy, which is the actor, and we have the critic, which is a value function, which is the critic. Okay, now there's a problem. Monte Carlo estimates have high variance, mentioned this already. And the bootstrapping actually that we use in the value learning with temporal difference learning introduces bias, since the value function might not yet approximate the true expected returns. So I want to ask, do people know what bias means in a statistical sense, as a like a mathematical term? Hands up if you know what bias is. Okay, just very few people. That's important though. I think yesterday or the day before I said Bayesian theory. There were only like 2 or 3 people who knew about Bayes. You need to know about Bayes for sure. Bias is another very important term in statistics and statistical learning that you should learn about. It means that your process will converge to an average estimate that is actually has an offset from the true average. That's the bias basically. And here we have a bias because when we do temporal difference learning and we have our bootstrapped target, which uses the estimates from the other places, that target might be wrong basically. So there will be this bias that's induced. And how do we address that? Well, we use something called n-step returns. This is something, it's a little bit more advanced, but I think I want to mention this because it's very important in existing state-of-the-art algorithms to get them to work well. So with what does it mean? We can basically now generalize our definition that we just saw in the earlier slide by not just having the immediate reward and then bootstrapping from the value of the successor state, but actually we now can do a sample of maybe the immediate and the one after, and then the one after, let's say the next n rewards. That's where the n-step return comes from. And then we bootstrap after that nth reward. And that's where this comes from, the ST plus 1. So you can see how this opens up a whole range of family of algorithms. You can have one-step returns, which is the standard definition for Q-learning. This is what you saw here. One step, one reward, and then bootstrapping off the successor. Or you can have 2-step, 3-step, or n-step. And that's basically the generalized definition here. You have n steps, which is summing over the next n rewards, and then you're bootstrapping over the using the value in the successor state there. And what this allows you to do is you can interpolate between TD learning, which was when this was 1, and Monte Carlo reinforced learning, which is when there was no bootstrapping here, and n basically was the entire length of the episode. And in the next slide, we're going to show some interesting graphics that actually show the trade-off profile. So it looks like this. Let me explain what this means. So on the x-axis, you have the different ends that you can just pick as an example. So 1-step, 2-step, 3-step, and so on. 1-step is just the standard Q-learning approach that you saw earlier today, and you can have any number of steps you want. And then at the extreme end on the other side is Monte Carlo, which is when you have the full episode and there's no bootstrapping. Okay. Then there's now 2 things we're showing. First of all, there's variance. So we know that for Monte Carlo, there's very high variance because there's no bootstrapping, and the returns that we collect over time, they can be heavily influenced by the stochastic nature of the environment. And so we have a lot of variance. On the other hand, if you look at bias, for 1-step return, you have the maximum bias because there's only one actual reward that we sample. And then we already bootstrapping off the value from the next state. So if the value from the next state is wrong, then we have a big bias that we are basically backpropagating. And so there's now some trade-offs you can basically go so see from left to right in between these options here. And in this particular case, for example, you can see that for a 4-step return, which is what we often use in practice, 4 or 5 steps, we see that the variance is kind of minimized, at least in this particular example. And we also have a much lower bias. Not the absolute minimum bias, but it's lower than the maximum here. And this tends to be working well enough. So we find in most of our applications, we end up using something like 4-step or 5-step returns, and they kind of tend to work best for us. We never really use 1-step returns, which is more like something that you teach students when they first learn about this. Okay, I think this is important, and you can play with this yourself. Clearly, you can just plug in different numbers. You can create these plots yourself or your training curves. And you can really see the differences that these things make, these kinds of hyperparameters. Okay, lastly, there's more refinements basically that you can think about. I think I'm almost running out of time for the first half. There's an idea called advantage actor-critic. It's just another way of defining this. I think I'm going to skip over this. You can look at this. A2C is one of the important actor-critic algorithms in deep reinforcement learning. Again, I think I'll skip over this. PPO is probably the most important deep reinforcement learning algorithms. Let's spend a little bit more time on this. PPO, if you look at any research paper these days in deep reinforcement learning, it's very possible, very likely that they have one baseline at least, which is actually using PPO or building on PPO or something like that. It just tends to be, it's just a really robust algorithm that works quite well in a number of cases. So what does PPO actually do? Let's spend a little bit more time here because it's doing something interesting. Policy gradient methods can cause significant shifts in the policy with a single update. Okay? That's what I explained earlier with neural networks. When you have a neural network input-output relationship and you've changed the parameters inside, you can actually change a lot of things that the network is doing. So if you update for one particular input, it can actually change the outputs for all kinds of inputs. That's just the nature of deep learning. And that's actually a good thing about deep learning, but it can also be a problem in the learning process. It's a good thing in terms of the generalization capability, but it can be a bad thing if things change a lot and they're hard to track. So the interesting idea with PPO is that we want to limit the change of the policy in a single update. So we have this idea of a trust region, a region that we kind of trust, where we say, okay, I don't want to allow the policy to change this much, but I think I want to allow it to change at most this much. That's what that means. I trust this region. It should be okay if you change by at most this much, okay? Rather than just letting it do super crazy changes. That's kind of intuitively the idea of what PPO does, the main idea. PPO itself is actually a proxy algorithm for another algorithm that came before that from the same authors called TRPO, Trust Region Policy Optimization, but it was very difficult to implement and had a lot of complicated theory, and PPO came out after to make it just much simpler and is very much simpler to implement and works almost just as well. So PPO stands for Proximal Policy Optimization. The name proximal comes from this trust region idea that we want to be in the proximity of where we currently are and not move too far. And computes a surrogate objective to limit the change of the policy, which looks like this. Okay, the loss function now has, it's explained in the next slide. It looks like this. This is the same loss function that I just showed you. There's a few elements here we need to understand. There's this row here, which represents the importance sampling ratio. Remember, importance sampling is, did we discuss this in the earlier lectures? I think I'm confusing this with my talk I did somewhere else yesterday. But importance sampling is another statistical technique that just uses the ratio of action probabilities from your actual policy and from a behavioral policy that is used to collect the data. Pi beta represents the behavior policy, which is actually used in the environment to collect the data. And epsilon is a hyperparameter that determines the allowed change of the policy. So that's what I just meant, where we only want to allow it to stray this far, but not crazily. That's defined by this epsilon parameter. And basically, if you look at this up here, there's this clipping operation. Clipping is something you often hear with PPO. It means that if there's this advantage, we don't need to define this for now. It's just a function of the Q function. Then we want to say, okay, we're going to clip around the advantage by minus epsilon and plus epsilon. So that's like the region around it, the trust region. If epsilon, if the advantage or the Q functions here, we want to have this epsilon region around it, and we're clipping anything that's bigger or smaller than that. That's where this clipping operation comes from. And basically, that's what it does. It limits basically the amount of change that we can incur. Here's the full pseudocode. I think I'm gonna leave this for your own enjoyment to digest this in your free time. Let's look at some results instead. So here's again the LBF, the level-based foraging example we saw earlier, where there's one agent and one apple, and it's just single agent, and the agent has no level, so it just collects that apple. There's a few algorithms we compare, three different ones. There's the blue line, which is reinforced. This is the one that uses the sample return that I just showed you. Then there's A2C, advantage, Actor-critic. This is something that I just skipped over, but it's, just assume it's another algorithm. And then there's PPO, which is the thing we just saw, which uses the clipping operation to minimize or to constrain the change in the policy. And you can see that, they have different success, I guess, in the learning. Reinforce learns relatively slower. It's suffering from, the idea that there's variance in the sample returns. And then there's the orange line, which is advantage Actor-critic. And then there's the green line, which is PPO, which works the best here. And in fact, in most of the algorithms, most of the time when we play with this, we find that either PPO or A2C works best. It kind of depends a little bit on the properties of the environment. But it just it turns out that in this particular LBF setting that PPO works best. We do sometimes find that A2C works better than PPO. But they tend to be kind of close anyway in many examples. Right, so but PPO, if you need to make a choice about a baseline algorithm in deep reinforcement learning, probably PPO will be a good starting point that already does something useful for you. Okay, this is now the last thing I want to mention, I think, before we get into the break. And then after the break, we're going to move into the multi-agent part. So there's just 2-3 more slides here, which is talking about this idea of concurrent training. And we're going to skip over, there's not going to be mathematical details. It's more about conceptual, how you actually train this to collect lots of data points. So policy gradient algorithms rely on policy data, which raises the question of how to deal with correlation in the data and how to increase sample efficiency. So there was a question earlier about that. And I guess now we're getting to your question there. Oops. And so the idea with this concurrent training is that we want to basically train multiple versions, so to speak, of the policy, or have multiple policies run in parallel to collect data points, so that we break through these correlations that I mentioned earlier in DQN. So we speed up training by getting more samples in parallel, leading to better gradients and breaking the correlations of data. There are many ways to do this, but we're going to focus on the synchronous and the asynchronous approaches, which are quite similar in nature, but one basically does synchronous time steps, and the asynchronous approach means that we have actual parallel threads in your implementation. They can run beside each other. So that's what we're going to be looking at, and then we get into the break. So first, the synchronous training. The idea is now that we have basically multiple threads, and they basically each have a copy of the same environment. So if we do level-based foraging, there will be now 5 level-based foraging environments. And in this environment, we have the same policy 5 times. And basically, they all get to choose independently in action in their copy of the environment. And we're saying it's synchronous because they all need to finish choosing their action. And then when they all finish choosing their action, basically gets collected and then moved up into the optimization layer, which is up here where the vectorization happens. And basically all the data points from those 5 different agents is then aggregated into the policy gradient. That's why it's called synchronous parallel training, because they're actually not really parallel threads. They just choose their action in parallel, but then they need to still wait for, basically, we need to still wait for all of them to finish, and then we collect those actions, and then we use those actions to compute our loss functions that we defined earlier. Compare this to the replay buffer that we saw. In the replay buffer, we actually store a lot of experiences in our set, and then we just randomly sample from that set, and that breaks through the correlations. Here we have a bunch of agents that choose actions in parallel. And by letting them all choose actions in their independent environments, they also break through the correlations because their individual observations will not be correlated anymore. So it's a different way to break through these correlations. I think that gets to your question that you had earlier. Okay. And now there's the other idea, which is the asynchronous training. This is when these threads are actually parallel threads that run in parallel in your machine. So we run, again, a number of threads, let's say 5 LBF environments. They're independent copies, and they actually run their independent policies independently from these other threads and collecting their data. And this data is then periodically stored in some buffer where it's used to update the policy. But the policy then, after it's been updated, is copied back into the threads and then used in all of these threads, basically. Okay. Lastly, there's a slide about observations of states and histories and so on. I think this is the very last slide. Remember yesterday, when we introduced partially observable stochastic games, I mentioned that there's this problem that we need to keep a memory functionality to understand what happened in the past. Otherwise, the observation that we have in this point in time might not actually show us everything that's important. So we want to collect and memorize. And with deep learning, it's actually kind of easy to do. With deep learning, you can do something called recurrent layers. So it's explained here. You cannot see this here because of the projector colors, but this is the partially observable level-based foraging where there's a square here, and that's supposed to represent that the guy can only see what's in the square, but not what's outside. So the agent needs to remember what's happened before. With the feed-forward neural networks that we've been using so far, they have a constant input size, and they are not actually natively able to gather these past experiences. You'd have to do tricks like zero padding, which means you know already how many experiences you have for your whole episode, and you add a gigantic input layer into your neural network and add lots of zeros, and then replace those zeros over time with the observations. It's not a good way to do this. It's like a basic naive way of doing this. The zero padding is not the right approach. Instead, what you can do is what's called recurrent neural networks. Recurrent neural networks are basically an idea where there's a recurrent layer at the input. That's where the name comes from. And when you add one of the inputs, it actually changes an internal representation that then basically is used again for the next input. So if you have observations and you feed one observation from one time step and then the next observation and so on, it's memorized internally through this recurrent layer updating, basically. And by doing this, if we train a network like this, it can actually be trained to do this inference process that it actually memorizes past information if it's important for the task. Okay, now we're at the end of that lecture. So just in summary, before we get into the break, we started by talking about deep Q learning, which is one of the most foundational algorithms in deep reinforcement learning, right? So it's the idea that we extend Q learning, but they actually have neural networks now that represent the Q function. And we saw that we needed to do a little bit of some extra things to make it stable. We did the replay buffers to break through the correlations, and we did the target networks to make it easier to bootstrap from the values. Then we moved into the policy gradient algorithms, which are based on the policy gradient theorem. These things do not maintain value estimates. Instead, we have a direct neural network that represents the policy directly. And the policy gradient theorem gives us a description of the gradient that we use to update the parameters directly of the policy. And there's many ways to instantiate this. We looked at one particularly simple one, which is reinforce. Okay, this is when we do a sample return. We then looked at some other more sophisticated algorithms, actor-critic algorithms, which maintain both value functions and parameterized policies. So they combine both of these ideas. And then we lastly looked at these different ways of concurrent training, synchronous and asynchronous. And those are maybe the most important ideas in a nutshell in deep reinforcement learning that you need to be aware of if you're going into this field. And of course, there's a lot more going on. There's a lot of state of the art. There's lots of tips and tricks and more sophisticated ways of doing stuff. And you can read lots and lots of papers. But I think this is the core knowledge you need to have. And it's all described in the book in chapter 8. And the deep learning is in chapter 7. So we're going to go into a break. I think let's maybe come back in like at 11:50, more than 20 minutes. That should be okay. And the next thing we're going to then start is our journey into multi-agent deep reinforcement learning. This is really where we want to go, right? But before we can get there, we had to talk about this stuff. So we're going to start talking about multi-agent deep reinforcement learning after the break. Before we do the break, maybe should I see if there's any questions? Any questions? Yes.
So just quickly to understand, how does PPO ensure that the update is within the trust region? Is it like that it does not update beyond a certain value, or some of the parameters are fixed and then only some of them are updated? So what's the...
Yeah, it's through this clipping operation here.
Okay.
Let's see here. So it's this thing here. There is a this is our hard parameter epsilon, which defines how far we want to be able to stray away. This is the advantage. It was defined earlier. I skipped over it, but basically imagine it's something like a Q function. And it's used as for the definition of the loss function. And then there's the rho here, which represents the importance sampling ratio. It's just a number basically that we can compute by doing the ratio of the policy for the probability it gives to this action and the behavior policy that it gives to the same action. So the clipping operation now means that we are basically clipping this ratio here to be between these two. This defines the range basically. It needs to be in between. And then we multiply this with advantage. And it means that the advantage is now constrained to be in a particular range. So basically, it's a way to clip the magnitude of the advantage that we do in the loss description. And intuitively, that's what I was trying to explain. If you want to think about it more intuitively, it means that if this is where we currently are with our policy, we don't want to allow it to go crazy like this and this to change, because this creates problems for the learning. We wanted to allow it only to go a little bit away from it to make sure that things do not get too crazy, and then it's easier to track. That's basically what this clipping operation does. It maintains it basically like that.
Thanks.
Make sense? Okay.
Two questions. The first one is about the asynchronous training.
Okay.
Wouldn't we update the policy with off-policy data? And is that a problem?
No, because all of these threads run the same policy. And when they are finished collecting the data, it gets passed into the policy update. And then when the policy is updated, it actually is copied back into the threads.
Then what's the difference between this one and the synchronous one?
With the synchronous one, it's the difference is that these things are actually running on parallel threads in your implementation. But with the synchronous one, these ones are synchronized in the sense that they take one action basically, and they need to wait for one another. In that sense, there's a synchronization going on.
Okay.
So it means that you can actually run this without actual parallelization in your machine. You know, because for example, if you implement Python, Python does not have very good support for parallelization. It's kind of clunky and not very efficient. C++ has excellent support for parallelization. So probably depending on what your language is and so on, I would choose one or the other, depending on which one is more convenient to implement.
And for the synchronous training, when you meant difference in environments, do we mean the same environment with the exact same seed and then collect data?
No, different seeds.
With different seed?
Yes, they need
Okay.
to be different, yeah.
Thank you.
Okay, question there?
This one is online.
Okay.
Regarding DQNs, we use the target network to make learning of the target more stable. However, if we begin with very poor Q values in the target network and we keep using them for a set interval to learn, doesn't that slow learning down?
If we give them I mean, the target network is basically tracking the real network. So there's no such thing as giving it worse values than what the real network actually has. Like the real network is copied into the target network. So I'm not sure if I understand the question. Maybe the person can add more information into the question.
Is writing. Well, I have another one. Wait.
Okay.
In Actor-critic, could we use off-policy experiments to update the critic, or we are still restricted to on-policy ones? Are Actor-critic algorithms on policy or off policy?
No, so if we do the value estimate, there would be an on-policy update then for the like we did similarly as in SARSA, basically. I think there was a question here earlier, so yeah.
In asynchronous training, how do we aggregate gradients or policies of local, let's say, multiple threads into the global agent policy.
So I think it's described here. So every thread separately computes a loss and the gradients to optimize the parameters of the network. But the gradients that are computed in these threads, they're basically they're passed into the central network, and they can be averaged. These gradients from the different threads can be averaged then, and then still a well-defined gradient.
As if it was federated learning, for example.
Federated learning.
Like
Yeah.
what happens?
I don't know so much about federated learning, to be honest. I think federated learning, doesn't that mean that if you have one big neural network, you have different workers that optimize parts about the network or something like that? I'm not sure.
I think you have local models which minimize their losses, and then they average the weights and send it to the global model, which then resends the improved weights to the local. So
it sounds like it could be similar, yeah. I don't know so much about federated learning. Okay, any more questions here before we get into the break? There?
Yeah. We normally see that policy gradient algorithms are quite good when the action space or the state space is continuous. But the formulas, the mathematics that we saw, that change with that into consideration, or it's the same when they discrete on continuous space or action space?
You mean the mathematics for the policy gradient theory?
Yeah. Does it change?
Let's see if we can go back here. Okay, so you can already see immediately that this does not apply to continuous controls, right? Because we're doing these sums over actions. Sums over actions here. And also the states will be discrete as well, which typically is also not the case in robotic control. So the way to make this then work is to replace this with integrals. But to be honest, now that you bring this up, I'm not sure if I actually have seen anyone do this yet, where they replace it with integrals. Yeah. I mean, typically, once you do these replacements, then a version of the same result would hold, because the integral is just the analog to the sum. But actually, I don't feel like I know a particular paper I can point you to where they've shown this, to be honest. Yeah, interesting. Maybe I need to look more into this. Yeah. Question there? Okay, interesting. Maybe you should send me a link to that paper if you don't mind. Yeah, if you can still find it. Okay, good. Yeah, perfect. He answered your question then.
Okay, the girl from the first question answered. She's saying, what I mean is that if the initial network has poor values, which are copied into the target one would think that using the target network does maintain those poor approximations during more iterations.
Yeah, interesting. Yeah, I guess that is an interesting point. And probably there would be an effect like this, except this effect would be washed away fairly quickly, because there will be an interval that's not too large anyway where the hard copy is happening. So as soon as we hit that interval where the hard copy happens, then any effect like that would disappear. And maybe this effect also wouldn't be... Yeah, actually, maybe this could be an interesting investigation, I'm now thinking, based on this question. Maybe there could be a master's project for master students here, if you're looking for a project. If it is the case that there's not a paper ready that's investigated this, which I don't know, maybe there's an interesting opportunity where you do a little investigation as an undergraduate or master's project to investigate this effect, and then you can play with the interval length. And if you stretch out the length, you give it more chance for an effect like this to happen. And you need to somehow find a way to badly initialize the values. I'm not sure exactly how you would do that. But yeah, maybe this is an interesting project. So maybe that's what I should say to the question going back there. The answer is I don't know exactly what, but maybe it would be an interesting project to try out. Okay, good. Then I think probably good to wrap up. So see you back. Well, we've used up a bit more time now. Maybe see you back at 12, if that's okay. Yes? Yeah, at 12. And this is just the beginning. So a lot of this material will actually be covered tomorrow, but we're going to start today, and then we just see how far we can get. So this is another set of slides you can find on the book website. This is the part 1. There's also part 2. We're going to try and cover this tomorrow as well. Okay. works. Okay, so just wanted to check again, were there any last remaining questions from the DeepRL lecture part that we just had before we move into this part? Were there any more questions? I don't see any hands, so I guess we are okay. As I say, now we're moving into the multi-agent DeepRL part. Finally, we're getting to the thing that we really want to do, right? That's why you're here. The multi-agent DeepRL is really why you're here, but we had to learn about a few other things first before we got to this point. And this is, the biggest part of the lecture, also of the book, of course. There's two parts I mentioned. Part one, we're going to start now. We won't be able to finish those slides today, I think, but we're gonna see how far we can get, okay? And we'll take it easy. I want to make sure you have opportunity to ask questions. We can have a conversation, and don't be shy. Like, just raise your hand if you have an interesting question. Other people might be interested as well. Okay. All right. So here's the book. Make sure it's really hard-coded in your head. Make sure you don't forget about it. Good. So here's the lecture outline. There's a few things we're going to try and cover. Training and execution modes, just some very simple basics. I mentioned a while ago that this idea of centralized training with decentralized execution. That's part of this conversation. We're going to talk a little bit more about that. And then you remember we talked about this idea of independent learning yesterday, right? Independent Q learning, for example. So you can actually do the same thing with deep reinforcement learning, where you use some of these single agent deep reinforcement learning algorithms that we just talked about. And you make them independent learners, just like we saw yesterday. Then something more interesting, we're going to look at multi-agent policy gradient algorithms. So we just had multi-agent, we just had the policy gradient algorithms, and we're going to make them multi-agent. Not sure. This is maybe a typo here. This line shouldn't be here. Okay, already on the outline slide, I'm finding something I need to fix. Sorry about that. Let me add a note. It's probably copied over from the previous lecture. And then at the end of this part of the lecture, there will be value decomposition methods, which are a really important class of algorithms in multi-agent deep reinforcement learning. And some really interesting works happen there. Okay, let's get into the training and execution modes. I'm going to go through this slowly. So we distinguish between these different modes in MARL. So there's training. Training is when we optimize the parameters of the policies that we are, trying to learn. And then there's a question, okay, what conditions do we actually have during training? What opportunities for data sharing, information sharing, experience sharing, and so on, parameter sharing and whatnot, do we actually have during training? Because this might be different from the situation during execution. So now you want to ask what information and gather, like information sharing opportunities and so on, might we have when agents are actually finished with the training, finished with the learning, and then now they get executed on the field in the deployed setting. So the way you can imagine this is that during training, this means that when we do our updates, your policy updates and so on, and we change the parameters, and execution basically means after training. No more changes, no more updates of the policies. They're fixed now, finished with the training, but they now run in your application, in your system, whatever it is you're doing. Your robot is now on the way. And the situation might be different, right? So during training, we might have opportunities that we do not have during execution. That is the idea. And I think we need to be aware of these differences because there could be opportunities to exploit here. Okay, just a reminder here. We've seen two single agent reductions of the MARL problem. We talked about that yesterday. There's the independent learning. Each agent learns its own policy independently using only its own data. And basically that means that we have decentralized training and decentralized execution, right? During training, there's nothing shared already. They just do their own version of their single agent RL algorithm. And it's the same during execution. There's no difference in the conditions there. Then we saw yesterday centralized learning, which is this other single agent reduction, where there's a single central policy that learns to choose join actions to control all the other agents. And so here it's different now. Here we have centralized training because the central learning algorithm has access to all the information from all the agents. And it also needs to be executed centrally because after training, it still requires that it sees all the information from all the agents and that it gives actions to all the agents, okay? So basically what this means is now we have a mapping. This independent learning that we talked about, the way to map this into this training and execution terminology is to say that this is involving both decentralized training and decentralized execution. Central learning, on the other hand, involves central training and central execution, okay? Basically, that's how we map these ideas from yesterday into these two concepts of training and execution, which are important for deep learning. But the interesting thing is now we have a new opportunity in these deep learning approaches, which is centralized training, where we have the opportunity to share a lot of information and other mechanisms, but we're training in a way where after training is finished, we can still run our policies in a fully decentralized fashion where they do not have access to this experience and parameter sharing and so on. And that's an interesting combination of these two things, right? Okay, so let's first look at independent learning with deep reinforcement learning. Just to get that out of the way, it's very basic. So as a reminder, in independent learning framework, each agent I lands its own policy pi I, using only its local history of observations and treating the effects of other agents as part of the environment. Right, so we talked about that yesterday. I think there were a few questions from you, and this idea, okay, what does it mean that we actually just treat the other guys as part of the environment? It means that we do not have any explicit representation of the fact even that there are these other agents. They're just noise in the background. There's something going on in the background, but I don't know what it is. It's just part of the environment, okay? That's what that means. So from the perspective of the individual agent, the environment transition function looks like this. This is just a repeat of the definition that I showed you yesterday. Remember in your game, in the stochastic game, this is the state transition probabilities, where for a particular state and for a particular join action, you get the probabilities over the successor states for the next time step. This is part of the environment description. But now we're actually defining this T from the perspective of agent I. That's why it's now a TI. And here, this now looks different, right? So because we now define this transition function to only depend on the agent I's action and not on the actions of the other agents, we need to basically sum them away. We need to marginalize them away. That's why we sum out over the actions of the other agents. Minus I is everyone except I. And then we construct the join action by combining our action I with the other guys. And we multiply this with the probability, the factorized probability, that these policies of the other agents would actually take this particular action. Okay? So we use this transition function from the game and we marginalize over the actions of the other agents, which are not I, and take the product with the probability that they would actually take the action. So this is almost like an average transition probability where we're marginalizing away the actions of the other agents. And this gives us this distribution over the successor states that only depends on the action of agent I. But if that is the case, then because the policies of the other agents are part of this definition of how agent I views the environment, if those policies change, it means that from the agents of the agent I, from the perspective of agent I, this whole expression becomes non-stationary. See what I mean? That's what we talked about yesterday. Is that clear for everyone, what this means in terms of non-stationarity? Okay, well, it's just a repeat from yesterday. So now the question is, can we do this kind of independent learning like we saw yesterday, where we used independent Q-learning? Can we do this with these deep reinforcement learning algorithms that we just introduced today? For example, earlier we talked about DQN, reinforce, and so on. And it turns out, yes, you can do the same thing, of course. So let's look at two examples, independent DQN and independent A2C, which are two of the algorithms that we looked at. Okay, so here's the pseudocode for independent deep Q-learning or independent DQN. We initialized n value functions or n value networks corresponding to the different n value functions. We initialized the n target networks. You remember the target networks that we introduced earlier. We also initialized the replay buffers, one for each agent. So you see that everything is basically multiplied by n, for the n different agents. Then we go through our training. We collect the observations for the different agents. Every agent has its own observation. And then for each agent does its epsilon policy gradient, epsilon greedy action selection. With the probability epsilon, it's choosing a random action. Otherwise, it's choosing the greedy action. We apply the join action. We get the rewards in the next observations. And then we do our updates independently for each of the agents. So this idea of independent learning becomes most clear here when you see that everyone is doing their update independently of the other agents. inside this block here, there's no reference to anyone that's not agent I. So agent I does only its own data, its own updates. It doesn't refer to any of the other guys. And that's basically what it means to do independent learning. Yesterday, when I showed you the pseudocode for independent Q-learning, it was actually simpler than this, because I just showed you the definition of the pseudocode from just purely for how agent I would actually run this. Here we actually combine this pseudocode for multiple agents, which is why we have this for loop here. Okay, we have a for loop here for the agents there, we have a for loop for the agents here, but basically you can just remove this for loop and just do this once and then copy the same algorithm independently for each of the other agents. It would be the same thing. So that's why it just looks a little bit bigger here. Okay, that's independent DQN. Straightforward. Makes sense for people? Do you feel this makes sense? Okay, not getting any questions, so I think it should be clear. So this is almost identical to DQN, except that we now have N agents. Chapter 8, which it says here, is just refers to the lecture that we just had, which is the deep single agent reinforcement learning. The replay buffers contain off-policy experiences due to the changing policies. That is already the case for the single agent case, what we just had. And in MARL, the policies of all agents are changing, so the training can become really unstable. And that's what we just refer to here when we say that from the perspective of individual agents, the transitions appear to be non-stationary if everyone keeps changing their policy. You know, and that happens when you do independent learning. Okay, here's another pseudocode, just as another example. This is for Advantage Actor-critic, A2C. There's another algorithm that I skipped over earlier. I think I'm going to skip over this here as well. You can sort of take your time back at home to digest this in a little bit more time. But it's just another deep reinforcement learning algorithm, which is actor-critic. So you're training an actor and you're training a critic, basically, using this advantage definition. But basically, it's similar there again. It's almost identical to the single agent version that was introduced earlier. And you can use the other algorithms that we looked at, like reinforce and PPO, just as well. You make it independent reinforce or independent PPO. It just means that everyone is using their own copy of this algorithm and there's no sharing or talking or whatever with the other algorithms. Right. So as you saw, independent learning is a general concept that can be used with all kinds of algorithms, and you can just basically plug and play. What you do not get, though, with independent learning is nice guarantees that you actually learn something meaningful, right? Independent learning is just a concept where I say everyone does their own independent version of the algorithm, but there's actually very little theory that shows you that when you do this, for example, independent DQN, they actually guaranteed to learn anything useful at all. It's very empirical in the sense, right? It's like a plug and play kind of thing. But still, in state of the art, I find, based on the research in my group, we've done this for a number of years, we find that basic baselines that use independent learning tend to be kind of strong baselines still in some applications. And we also found that in some environments, we did a benchmarking paper that was published at NeurIPS a few years ago. We found that some very basic independent learning algorithms, like independent A2C, performed better than some really super duper fancy state-of-the-art algorithms in certain environments. And what it tells us that some of these fancy algorithms, they're really designed to exploit certain structures in the environment. But if these environments don't actually have these structures that they expect to see, then the performance drops. And it's just a trade-off. It's a version of no free lunch, right? It's what you often learn in computer science. Anyway, so here's another reminder. Let's look at some challenges. I just appealed to this a little bit, but it's a good reminder. Multi-agent reinforcement learning algorithms suffer from certain challenges that are specific to the multi-agent nature. We looked at this yesterday. Of course, there's already challenges from the single agent part, but let's look at these multi-agent challenges. So there's the non-stationarity. This is what I just showed you in the definition of the state transition probabilities. This is even made worse when the policies of all the agents are changing, and in particular in independent learning. Then we talked about equilibrium selection yesterday. This is when a game might have more than one unique equilibrium, and the question is which of these equilibria should the agents actually converge to, and how do they actually agree that they should converge to one and not the other? Because different equilibria can entail different expected returns to the different agents. It's important to keep that in mind. Multi-agent credit assignment is this idea that it's not just important to understand which of the past actions were important, but whose actions were important as well, right? We talked about that yesterday with the level-based foraging example. And then scaling to many agents is still a big deal in today's research as well. And so based on these challenges, we're going to go into the centralized training with decentralized execution now. Centralized training with decentralized execution, or CTD, is a common term for that, can actually be useful to address several of these challenges. And that's because when you do have the opportunity to train in a centralized way, you can do certain interesting things, like you can share a lot of information, you can share coordination mechanisms, you can share parameters and so on, which can make your life a lot easier. And then you might be able to address some of these challenges much more effectively than if you had to learn completely independently, which is what happens in independent learning. So here's one example. This is called the multi-agent policy gradient or multi-agent policy gradient algorithms. So you just learned about policy gradient algorithms in the single agent case. And we want to do something just like that, but for the multi-agent case, which means that we have these parameterized policies with neural networks, and we want to modify the parameters directly in these neural networks. Okay, here's a reminder from what you just saw earlier in the lecture. So we have this policy gradient theorem, which looks like this, right? There's a function j for the policy parameters phi. We take the gradient, and that's proportional to what you see here, where we sum over the states. There's the state visitation frequency, you sum over the actions. You multiply the action value with the gradient of the policy at that action point. So it's just a summary, and you can actually, pull a lot of these, pull these sums into the expectation, which leaves you with this that you can then instantiate to get the algorithm. For example, in reinforced, we instantiated it by replacing the Q function with the sample return. So far, so good, right? That's just a recap of what you just saw literally an hour ago, basically. And the question is, can we do something like that for the multi-agent case? Does this also hold in MARL? Yes, with minor modifications. Well, sometimes minor, sometimes they can be bigger, but let's start with the minor ones. Okay, so here's one approach. The expected returns of agent I under its policy pi I depend on the policies of all the other agents. That much you know, because that's all we talked about when we introduced the solution concepts. The whole idea being that my returns depend on what you're doing. And so in the multi-agent policy gradient theorem defines an expectation over the policies of all agents. That is basically the big difference. There's no longer just a single agent, there's now multiple agents. So if you look at this here, this kind of looks similar to what you just saw. There's our J function here with the parameters for agent, J function with the parameters phi for agent I. So that's new now. There's a I index because we're doing this for one agent I. And here we take the gradient again. There's now an expectation where we actually have the full histories that are distributed according to this distribution here. And now we see that there's actually both in here. So there's not just agent I's action. This is what we had before. We now also need to sample the actions of the other agents, which is the minus I. This is now the new thing that we show in the expectation here. Then we move into the expectation. You can see that again, we have our Q function as we had before. But now a crucial difference is that the Q function is defined not just over agent I's action, but actually over the joint action. So it's a joint action Q function, or as we call it later, a joint action critic. Okay, it assigns values not just to my actions, it assigns values to all of our actions and the combination of these actions that when we pick them. And then we multiply that with the gradient of the policy parameters for that particular action that we're looking at here. So that was step by step, basically how we add bits and pieces to make the single agent policy gradient into a multi-agent policy gradient. Those were the modifications, basically. So now we derive a policy, we derive policy update rules by finding estimators for this particular part of the definition, which is just what we did before. Before, when this was single agent, you saw an example where we used a sample return, and this was the reinforced algorithm. Now we can do something similar and also other techniques, but designed for the multi-agent version of this Q function. So, okay, I guess we didn't see this because we skipped over A to C, but earlier, there was it showed that for A to C, it uses an advantage term, which is an approximation of this already. But you can also use sample returns or other kinds of approximations. Okay, so now it's something interesting comes into play. And that's now going back to the centralized training with decentralized execution. It gives us some new opportunities. In actor-critic algorithms, only the policy and actor is used during execution, and the critic is only used during training. That's because the critic is the thing that we use to do the bootstrapping. The bootstrapping gives us the update targets, but these update targets are, of course, only used during training. When we've done with training, we don't compute these targets anymore. We're finished with that. We only have the policy node that we execute, which is the actor. So the critic can go in the bin, basically, and we only need to keep the actor. What this means is that if we train the full system with the actor and the critic during training, then because we only need the critic during training, but not during execution. During training, we may be able to do things that we're not able to do anymore later during execution, but we might be able to do them during training. For example, sharing information. So what this says is here, the critic can be conditioned on the centralized information Z. Let's just call it Z here. It's a placeholder for all kinds of things, without compromising the decentralized execution. I really want to make sure that this is clear. So let me explain this again, what this means. We have a training process. During training, we may be able to share a lot of information, but maybe this is not realistic during execution after training because of certain constraints and conditions. But maybe in simulation, it's fine during training. And because when we use an actor-critic approach, the critic is only used during the training and not during execution anymore, that's actually fine because we can then throw away the critic. And as long as the actors were trained from the start only to rely on their local information, they will still continue to operate after training like they did during training. So, and that's a really interesting idea. It opens up all kinds of possibilities. So for example, this extra conditioning information Z, which was just a placeholder, could be things like a global state that is jointly optimized by all the agents together. Or in fact, during training, in simulation, we might actually have access to the ground truth state directly. And it doesn't matter because during execution, if the policies are only trained to reuse their local observations, but the critic maybe uses the global state, that's still fine because after training, we can throw it away. Also, the joint action might be available during training. You know, if they all tell each other what actions they're going to take. Joint observation history, they will be able to share during training as well, which they might not be able to share during execution because it requires communication and so on. And other things you could be doing as well. So let's look at the first idea here that actually shows this. This is called the centralized critic. This is called centralized because it can use centralized information, like if everyone puts all their information into one centralized place. There's a neural network here. It takes two inputs. This is the network for agent I, so it takes the history for agent I, and then there's some extra conditioning information, for example, the state of the world that we might be able to know during training. Then there's the internal computations going on in deep learning, and then it gives you as output a value function for the different kinds of actions that you care about. So now we can integrate centralized critics into multi-agent policy gradient algorithms. And remember, the Z could be things like privileged information like the state or shared observation histories. Here's an example. This is, again, for advantage actor-critic. I'm beginning to think maybe I shouldn't have skipped this. In my head, kind of felt like it would be fine to do this to give you more peace, but actually maybe I should have not done this. But it doesn't. It's not so bad. Advantage actor-critic is just an actor-critic algorithm that uses an actor and a critic. The reason why it's maybe a little bit more interesting is because it uses an advantage, this term called advantage. But basically, just imagine that it's an actor-critic algorithm that uses Q functions as well. I mean state value functions. So let's look at this. We initialize the n actor networks. These are the phi's from 1 to n. We initialize the n critic networks. These are now the theta parameters because they belong to the critics. We use phi and theta. And then we have our k parallel environments. Remember that we're doing one of these parallel execution schemes. In this case, I think it's, is it synchronous or asynchronous? No, it's synchronous because it's A2C. Asynchronous would be A3C. That's where the terms come from. Okay, so we're going through our time steps. We first collect a batch of observations for each agent and environment. There's these parallel environments, so we sample these batches. And then we have a batch of centralized information. This is the red line. This can be new now. So the centralized information, for example, could be that everyone shares all information with everyone else that they have, or like the state or some privileged information. Then you sample the actions from the different policies in the environments, in the environment copies, and then you apply your actions. You get your rewards from the different, after the different actions and the new observations as well. And you get your new updated centralized information for the successor state. Again, this could be the actual successor state or some other information. And then for every agent, you apply your computer loss function. So there's a difference in terms of whether the successor state is a terminal function, a terminal state or not, as we saw earlier for DQN. And we're basically doing this all to update the actor loss and the critic loss. These are the two important lines. Basically, we're updating the actors and the critics of the different agents. And the only important thing here really is to see is that we're during training able to use these centralized pieces of information, like the actual state of the environment, which we have access to during training. And when we do have access to the state of the environment, we can just throw that into the network, like here, if this is the network for the critic. It doesn't matter because after the training we finish, we don't rely on this Z anymore. Okay, let's look at one of these centralized critic algorithms in action. So this is a popular game that's often used in research. It's called speaker listener. Although I guess I would say it was used maybe a bit more often in the early days, a few years ago, and now it's maybe not used so much anymore, but it's still an interesting kind of domain. So there's two agents. There's one agent called the listener, and there's one agent called the speaker. And they have different actions. The speaker can send a message to the listener. And in this case, the speaker tells the listener where it needs to go. So go to this place, or this place. You know, that's what this message is supposed to show. So in this case, it's trying to tell the listener you need to go to this place. The listener doesn't actually see where it needs to go. It needs to learn to interpret this message. And what it can do is to navigate in the environment. So it has to move. In this particular version of the task, it actually has to move up here. That's its target goal. But it doesn't actually know this. It needs to they need to learn together to interpret that if the speaker says this, then the listener has to interpret this to say that, yeah, I need to go here. Okay, they need to learn this together, basically. They also need to learn that if the speaker instead says, this is your target location, the listener needs to interpret this and understand, okay, yes, I need to go here. Okay, they learn this sort of way of interacting together. Here's the results for two algorithms. One is independent actor-critic, and one is centralized actor-critic with the centralized critic. So this is now based on the multi-agent policy gradient. And you can see that the centralized critic actually gives it some interesting opportunities. So already during training, we are reaching better performance, and these are evaluation returns. So when we create each one of these points, it means that we fix training here, we take the joint policy, and we run a number of these full episodes and average over them. But when we run these episodes during evaluation runs, we don't actually have access anymore to this privileged information. So this is actually the performance we would get at that point in time if we finished training at that point in time, when we didn't have access anymore to this centralized information. So agents with centralized critics converge to higher returns than agents with independent critics in the partially observable speaker-listener game. Okay, so the same idea, of course, you can extend. So we looked at centralized state value critics, and they were used in the advantage computation there, but we can do the same thing for centralized action value critics. So Q functions, not V functions. That's why it's now, the output is now changed to Q. And the input has another bit, which is the action for the other agents. So similar, we can learn an action value function that receives additional centralized information Z. Again, this could be the actual state of the environment or a shared join history and any other information that they might be able to share. And then the output here is the values for the different actions that you can actually execute for agent I, against assuming that the other agents are executing their join action here. Okay, so why do we do this? But what for? Centralized action value critic can reason about the join action space. This is really important. Remember yesterday when I gave you this example of rock, paper, scissors, and where an agent was actually only using a Q function for its own action. And I gave you this example where there were two cases. One time I got +1 reward and one time I got -1 reward, but in both cases I picked the same action rock. It just depended on your action which changed. And if it's just a Q function that only evaluates my own action, the average looks like 0 between +1 and -1. But it's not right? It really depends on what the other guy is doing. It should really be -1 or +1. And in order to represent this kind of information, we need a joint action critic. This is now what we can do by attaching values to joint action combinations. That is the reason why we want to extend this now to these Q functions. So you can do some interesting things with that. For example, one idea that was quite impactful, but empirically it kind of doesn't work very well. I was highly cited, and like a lot of people looked at this, and then we started investigating it, and we found that actually it doesn't work at all in practice. And we sort of described this, and yeah, people kind of stopped using it after that. But before that point in time, it was kind of impactful. And it's because of the theoretical nature of this idea. And it just happens that in practice, it doesn't work so well. So what does it mean? Counterfactual reasoning is this idea that you want to understand the impact of the different actions. Remember that we had this problem of multi-agent credit assignment. I need to understand whose actions were actually important for this reward that I just received. Was your action important or maybe not so important? And counterfactual reasoning allows you to marginalize away the other guy's actions and see what difference it would have made. That's kind of the idea that why you do this. Basically, that's what this describes mathematically here. Okay, so now we have a computation here. This is again the advantage for a particular joint action after a particular history. It takes, first of all, the Q value for that particular joint action under the current parameters of the network that we have, and including any privileged information you might have, like the state of the environment. But it subtracts from that this counterfactual baseline. Remember this term baseline that we introduced earlier? We saw this in the reinforced algorithm. This was done so that we would reduce the variance. Now we have a counterfactual baseline, which looks like this. We sum over all the possible actions for the other agent, for our agent, because we want to marginalize our agent's actions away. And then we just take the probability that we would have picked that action and multiply that by the joint action value when we change only our own action to this particular action and keep the other guy's actions fixed. So basically, the way you can think about this is that I'm trying to remove my own action from what we've just done. And then I want to see how much that actually changes the value, basically, of the original joint action. If I can remove my own action and it doesn't actually change this value here, it kind of gives me a signal that my action probably wasn't very important for the reward that we just received. And conversely, if after this subtraction, there's a big difference here, then it kind of gives me a signal that probably what I've just done made an impact. That's intuitively the reason why we do this counterfactual baseline reasoning. So to look at this again in more detail, Q, as I explained, is the expected return when applying a particular joint action A. So agent I applies its action AI from this particular joint action, and all the other agents stick with their actions as well. Then the counterfactual baseline is the expected returns when agent I samples its actions AI from its actual policy, and the other agents continue to stick with their action. So we want to identify the contribution of agent I's action, which is what I just explained, and that basically helps you to address problems like credit assignment, which is the problem that we saw yesterday, for example, with the problem with rock, paper, scissors, or with level-based foraging, where we saw this example that some guys picked up an apple, but it's not clear whose actions were actually important. Okay, I think before I get to the next thing, I want to see, does this make sense for people? This idea of counterfactual baseline and how that might, at least in theory, be able to give you a signal to address the multi-agent credit assignment problem. Make sense? I'm not sure if people are just shy or if they actually feel it all makes a lot of sense. Okay, maybe now there's some questions. Okay, let's start with the first question.
It's for independent learning, the action value function.
No, it's not independent learning. Now we have this multi-agent policy gradient. So there will be things there's a centralized critic which uses this information Z, which could, for example, be the shared observation history or the state of the environment.
Oh, okay, for A to C, because in the former one was the value function. Okay.
Okay, yes.
Centralized value function.
Yeah. Another question there?
May you return to slide 12?
Slide
12, see?
slide 12.
Yes.
Okay.
It's a great slide. And I have a note and proposition that I have translated this notation to UML diagram, to sequence UML diagram. And if there is a person who would like to see maybe something in graphical notation, I may help you, because now it is already in my computer. And one more proposition, if, for example, you feel that there is difficult mathematics for understanding for people, and there are people for whom is more simple to understand this mathematics in UML, you may say me directly during lecture that translate this not to your UML notation, and I will do it in a minute, and maybe can present it in my notebook. As,
That's interesting, yeah.
Yes.
I think it's something like this could for sure be interesting for students if you have some sort of graphs like this to share.
Now I have this UML diagram sequence. You may say that you need other type of UML diagram, maybe it help. And in, because I heard that it was love in our hall, and if anyone would like, you may see now from my notebook, or maybe you may from some network, I may produce these diagrams quickly and share with those who would like. Maybe it will help you to.
Very interesting. Yeah. I think, yeah, please do send it to us by email. I want to share this with my co-authors. And then we might actually be able to put this into the slides if that's okay for you, like if it's easy enough to use.
But maybe we will ask other people to see this diagram and to compare formal notation and to compare graphical notation.
Okay.
And if it will be feedback that it is more convenient, for example, you may see it is difficult, please do it, and during lecture I will do it.
Yeah, nice. Yeah, that's a cool, that's an interesting idea.
Maybe now anyone wants to see this diagram and to estimate, will it help you or not?
I think what you could do is to actually post that on the Slack channel, and then people can look at this and give feedback. Are you on the Slack channel already?
I am not, but if you invite me,
yes, I think Jordi, if you can also invite her to the Slack, then you can post it there. Yeah,
gracias.
Thank you. Okay, was there another question here there?
For the counterfactual policy gradient, wouldn't the main, like one of the major causes why it fails be that it actually uses actions? Like it will scale terribly as we established.
Yeah,
right?
yeah, the scaling is already a problem with that. But even if you ignore that, even if the scaling is not a problem, you only do this with 2 or 3 agents, practically already didn't work well in our experiments. When we, for example, when we executed this in environments where there's sparse rewards. So most of the time they get 0, but only a few times they get a positive reward. This doesn't give you much signal to work with at all. It's just 0 most of the time. And I think, yeah, there's probably more analysis that could be done, but the community, after we did this work and then others followed up, I think we've sort of established that practically, even though theoretically this is interesting, practically it just doesn't work well. And I think maybe people need to follow up to explain why practically it doesn't work well. Maybe something is missing, you know, maybe something interesting is missing for the practical implementation.
And also in general, does it in practice make sense to use actions for centralized learning, because it will increase the complexity of learning?
So you're right. So if you have a centralized action critic, like a joint action critic, which is what we have here, then you in principle suffer, or you're subject to an exponential growth in the joint action space in the number of agents. And so that is a problem for scaling for sure. I would say, but maybe there's still opportunities where during training we might be able to exploit certain structures so that, you know, if there's sparsity in the interactions, then you can already have sparse networks and only some of the fields need to be filled, because most of the time I do not interact with you guys, I only interact with you, you know, this kind of sparsity and other structures. And people have tried to come up with smart ways of doing this. But if you don't do these things and you purely look at this, then yes, I think you suffer from the exponential complexity there for sure. Okay, so I think let's move on to the next thing. So now we're going to move to this other challenge. Right now, what I showed you was the joint action critic in order to address multi-agent credit assignment problems. And now we're going to look at one of these other challenges that we introduced earlier and yesterday, which is this equilibrium selection problem. So as a reminder, the problem is that many multi-agent games may have multiple equilibria, not just one, but multiple, even infinitely many. And the problem is that each one of these different equilibria may entail different expected returns for the agents. So there's differences between these equilibria. They're not all the same, and they need to pick one and stick with that one. So in such games, it's difficult for all agents to agree and converge to a single equilibrium. How should they do this? How should humans even do this, right? It's kind of hard enough already for us if you think about it, if we play some kind of games or do social interactions. So this is known as the equilibrium selection problem. And this is a big problem, not just in multi-agent reinforcement learning. This has existed for a long time in the game theory literature and is still one of the core, hardcore problems in game theory. It's just inherited by multi-agent reinforcement learning. So some examples I think that we saw yesterday. This is the stack hunt game that you saw, where you can get either the stack or the rabbit. There's another game. This is a common reward game, so that's why there's only one number. They all get the same. It's called the climbing game, and they have different equilibria, which are marked by these symbols here. So the cross and the double cross. There's first the Pareto-dominated equilibria. For example, for stack hunt, this is the equilibrium in the lower right corner. This is a deterministic Nash equilibrium, but it's Pareto-dominated, which means there's another joint action policy. There's another joint policy which makes at least one better off without making anyone else worse off, which is exactly this one here. Yesterday, we actually used this different term. We called it risk dominant, which means that if someone deviates from that, there's not so much damage as if someone compared to if someone deviates from here. You remember this terminology that we used yesterday. And then there's the double cross, which is the Pareto optimal equilibrium, which in this case is the one in the corner here. Similarly, we have different equilibria in the climbing game as well. And both of these are equilibria. There are well-defined solutions which are valid solutions. Both of these would be valid solutions. So but then the thing is, they're clearly different. If we're looking at the stack hunt, it seems like we should clearly take this one here. But most of the time, the algorithm would converge to the Pareto-dominated equilibrium, which is not desirable, if you care more about maximizing welfare, for example. So that's why we introduced this idea of Pareto optimality as refinement concepts, because you now can say, no, I don't just want a Nash equilibrium. I want a Nash equilibrium that's also Pareto optimal amongst the Nash equilibria that exist in the space. So that was this idea of refinement. And that's one kind of way to address the equilibrium selection problem in the sense of narrowing down the space of possibilities. But still, you may end up with multiple equilibria, and then you still have to find out how they should coordinate to find the right equilibrium. So here's an example in the climbing game for an equilibrium selection problem. Yesterday, we looked at the stack hunt. Now we're going to look at the climbing game. There are two equilibria. There's the Pareto optimal equilibrium, which is the double cross, which is at AA. You can see it's an equilibrium because no one has an incentive to move away in order to increase its individual reward. So it's a Nash equilibrium. And both agents get a +11. Then there's a Pareto-dominated equilibrium, which is BB. This means it's also an equilibrium. No one has an incentive to unilaterally move away from this in order to increase its reward. But there's actually another equilibrium which is better for both agents. So it's this one, Pareto dominates this one here in the center. But still, they're both Nash equilibrium. All agents would actually prefer the Pareto optimal equilibrium, right? That's what we should expect to see. But if we deviate from the equilibrium by any of the agents, it results in lower returns. So there's this risk of receiving -30. That's why it's safer for these guys to go to the risk-dominated equilibrium, which is in the BB space here. So that's the problem. Due to the risk of these deviations, agents often converge to the safer Pareto-dominated equilibrium. This is what we see here, and this is what we saw yesterday in the stack hunt game as well. Even though these are actually suboptimal because they could be getting other rewards by picking different equilibrium. So how can we overcome this problem? And there's one idea basically that I want to share, which is this idea of Pareto actor-critic. As the name says, it's an actor-critic algorithm. It's actually a multi-agent policy gradient-based actor-critic algorithm. And it uses this notion of Pareto optimality sort of baked into the definition of the algorithm. It's actually designed for a particular class of games, which we call no-conflict games. This is not a word that we made up. It's actually also from the game theory community, where they have all kinds of taxonomies for different types and classes of games. And a no-conflict game simply means that it's any matrix game where all the agents at least can agree on one preferred outcome, even though they might not agree on the various other joint actions in terms of relative preferences. But there will always be one joint action that everyone agrees. For example, in this case, we know that everyone would always most prefer this particular joint action AI. So this is a no conflict game. There's no conflict in the sense of what everyone thinks is best. Okay, so you can see that that's a class of games. And so in this case, that's what this defines more generally for all for stochastic games and partially observable stochastic games by abstracting over the expected returns. It means that for both of the agents or for all of the agents, there's one joint policy, or there's a set of joint policy that everyone would most prefer. So we can use this property. Basically, if we assume that we're in such a game, and we assume, everyone that there is such a thing as a joint policy or a joint action that everyone collectively would actually prefer to have, then we can kind of make this assumption that everyone is benign, everyone is kind of friendly. We don't need to assume that we are competing. We can already at least assume that there is such a thing that we would all prefer if we could do it together, like all doing the action AI in the example that I just showed you. So we can bake this into the algorithm, into the multi-agent critic. Agent I during training assumes that all the other agents follow this policy pi plus. Let's say that's like the friendly, benign policy that is best for agent I. Okay, I assume that you are going to do actions and policies that are best for what I actually want to do. And you will assume the same thing about me, that I will do something that is best for you. Okay, that's like an assumption that we're going to bake into this algorithm. We can make this assumption because of this no conflict game nature. So we can compute this pi plus for the other agents using a centralized critic that receives the joint action as an input. Okay, so pi plus is this policy that I'm assuming you're going to be using, which is the thing that you do to make my life to make my life as good as possible, basically. Like it's to do the thing that I find the most desirable. Exactly. So it chooses joint actions, which maximizes the value in my Q function if I choose a particular action. And so these are the actions for the other ones that are being maximized under this policy pi plus. Okay, and the same things these other agents are doing basically when they assume how I'm acting, that I'm also taking an action that they find most desirable. Make clear for everyone? Is that clear? Okay. So during training, agent I optimizes its policy pi I by minimizing the following loss. It looks a little bit bigger here, but actually it's not so complicated. So here's our loss function for our parameters phi I. This is for the agent I that we just now optimizing. And there's an expectation here. There's the action for agent I, which is sampled from its policy, and there's the actions for the other agents minus I, which now are sampled from this plus policy, where I'm assuming that these guys are doing things that I find most desirable. So we're basically plugging this into this policy gradient. Here we have our log function over the policy that we had earlier. Maybe I should actually move this at the end of the equation as we had before, just to be consistent. I think I'm going to make a note about that. It doesn't change the equation. I think I'm just going to move this part to the end because that's what we did before as well. Okay. Yeah, so that's as before from the policy gradient. And now we basically, how do we compute the advantage here, or the goodness of the action? In this case, we have this pi plus, the Q function for pi plus, which is basically over the joint action, defined over the joint action, which comes from the policy pi plus. And then we have our state value function, which is assuming that after this date, subsequently, the agents will follow this pi plus, which includes my own policy as well. Okay, so that's this idea of Pareto Actor-critic. It's an algorithm that we published in TMLR, which is a machine learning conference. We published this last year, I think, and just in time for this to end up in the book as well. And we thought this was important because it gives some really nice results. So here's a result in this climbing game that I showed you earlier. On the x-axis, you have your environment training timestamps. And on the y-axis, you have your evaluation returns. You want to be as high as possible. There's going to be two algorithms. There's Pareto Actor-critic, which is the blue line. That's the new thing that I just explained. And then there's centralized A2C, which is A2C using a centralized joint action critic. So you can see that A2C learns fairly quickly, but it's plateauing off here. Whereas Pareto Actor-critic needs a lot more time to collect the data to fill the joint action tables. But actually, then once it's done it, there's suddenly this learning period where it quickly identifies the Pareto optimal equilibrium. And we see this in a lot of environments, basically, where there's a lot of learning initially, where it's needing more time to collect the data. And then once it's reaching a certain amount of data, it's actually confident enough to jump towards this more desired equilibrium, which in this case was the AA joint action, the one that's more risky to achieve. Whereas in this case, the centralized A2C, it sticks with the Pareto-dominated equilibrium, which was the BB action that you saw in the climbing action, in the climbing game. So just to help you remember, if you look at this here, these are the two things we care about. This is the suboptimal Pareto-dominated equilibrium. This is the Pareto optimal equilibrium that we really ideally would like to have, that actually everyone finds most desirable. And yeah, that's what we end up reaching. So it's nice. And we tried this not just in these simple matrix climbing games. We actually evaluated this in much more complex games like level-based foraging and others, and saw that we had much better outcomes with this kind of approach. So just, I guess, to wrap up these explanations, A2C with centralized state value critic converges to the Pareto-dominated equilibrium, which is BB. That's what I just explained, gives 7 plus 7 per agent. Pareto Actor-critic algorithm, the one that we just introduced here, converges to the Pareto optimal equilibrium, which is AA, which gives plus 11 for the agents. And yeah, I guess, yeah, that's it. So the reason is, I guess the interesting thing to ask is, why is this taking so long here, right? Why is this taking so long to learn? Keep in mind that the difference is that Pareto Actor-critic actually learns a joint action value function, which has this exponential growth, which was mentioned earlier, right? There's a lot more information that you need to fill this function. Whereas with the centralized A2C, it uses the state information, but not a joint action critic. So it doesn't need as much data to actually learn initially, but it will prematurely converge to this Pareto-dominated equilibrium, and it's not able to recover from that because it doesn't understand this idea that there is multiple actions and they have an influence on each other in terms of the expected returns. Okay, so I think probably now is a good time to stop. Leave it at that point. We can continue here tomorrow and see if there's more questions we can discuss. And basically tomorrow we're going to continue here and also move into part 2, which has even more sort of interesting algorithms in multi-agent deep reinforcement learning. But tomorrow we're going to be continuing from here. So I just wanted to see, is there any questions about Pareto Actor-critic or these other ideas that we just introduced here? Or yeah, there's questions there.
In the architectures you've shown, the critic is always like it's not shared. Can the critic be shared across agents?
Yes, yeah, for sure. Yeah, parameter sharing is a very important mechanism. And in part 2 of the slides tomorrow, we'll talk about parameter sharing and we'll get back to that.
Okay. Thank you.
Online questions, I guess.
Where would Pareto AC converge to in the prisoner's dilemma?
So a prisoner's dilemma is not a no conflict game. There's not one outcome that is most preferred by all the agents. So the algorithm is not defined for that kind of game, basically, is the answer. Although I guess, I mean, you could still run it and then you can still see where it would converge. And the answer is, I don't know. We didn't try it for this kind of game because it's not a no conflict game. Any other questions there?
So it's about the PPO, which was in the first part. The trust region. So does it actually change during each iteration, or is there a defined trust region where the policy can?
It changes, yes, because it's actually the clipping operator, as you saw, is actually multiplied with the advantage term. So as the advantage term changes, for example, maybe it shrinks over time, then so does the region that is around it, which is defined by epsilon. Epsilon is multiplied with this term, so it will always be affected by the magnitude of that term. So it will like shrink basically. And that's desirable, right? You want the policy to become increasingly zooming in and confident basically in terms of what's a good region, and then I should try and stick around there basically, you know.
During the when you review the literature, you often see that we can apply this multi-agent reinforcement learning with cooperative agents and in competition. But I mean, do you have to like change something within the algorithms, or just it's because their words are like one negative and the other positive, and how would this work?
Yeah, so the question is, there's different types of games like common reward, zero sum, and general sum. And the question is, can you apply, you need to change something about the algorithms to apply them to the different settings. So it depends is the answer. Some algorithms are very general. They can work with any kind of reward function definitions. For example, if you have a centralized A to C, it just uses the state, but it doesn't have any assumptions about what the relationship in the rewards is. It works everywhere. But then an algorithm like Actor-critic assumes that at least implicitly that we are in no conflict games, which means that there's this added assumption that there's at least a joint policy that everyone finds most desirable, and it's baked into the algorithm. So it probably wouldn't make a lot of sense to apply this kind of algorithm to games that do not have this property. So you can see this is an example of an algorithm that achieves some really good performance, but it requires an extra assumption, you know, something specific about the reward functions. And that's how really the whole field operates. There are certain things that some clever people find about certain kinds of games they care about, and then they develop clever algorithms that can make the most of this kind of information, right? But then when you do not have this kind of property, no free lunch, it says that, you know, usually they might not perform then so well anymore. Yeah, but I think I would say apart from Pareto Actor-critic, all the other algorithms that I introduced up until that point, they can be applied across the spectrum in terms of reward functions. Yeah. Tomorrow, there will be other algorithms that, you know, also will be more restricted to certain classes. For example, certain value decomposition algorithms only work for common reward games and not for other kinds of games. So it's, you know, becomes more restricted. Any last questions? Some more online? Yeah.
Okay, it says, it looks like the algorithms take a lot of time to converge, several hundreds of thousands of steps for simple environment. This is something that is common in multi-agent reinforcement learning. Is exponentially more step consuming than regular reinforcement learning?
Yeah, it's common to all of deep reinforcement learning, not just multi-agent deep reinforcement learning. So it's just a known fact that deep RL, for various reasons, is not very sample efficient. Okay, many deep RL algorithms, even in relatively simpler settings, depending on hyperparameter settings for learning rate and batch sizes and neural network configurations and how you actually do the momentums and so on, and when you update the parameters, that can all have a big impact in terms of how quickly or slowly these algorithms learn, and you need to find out good settings. But even if you do find good settings, it often is still the case that they really do require a lot of data. And it's a nature of this idea that you have a neural network that is supposed to generalize a mapping in a state space that can be billions of states large, right? So it's not an easy task if you think about it. You need a lot of data to understand the right concepts at the right level of abstraction, and you know that can take time. In addition, there are certain things that are baked into these algorithms that just make it slow by definition. For example, back propagation through bootstrapping can be slowing down the learning because there could be bias, and it could take a lot of time for the bias to basically disappear. It needs a lot of data basically to catch up on the bias. Or if you have an algorithm that has a lot of variance, like reinforced, requires a lot of data to find the actual average point. So there are certain elements about the hyperparameters. There's certain elements about the size of the world, but there's also certain elements about how we design these temporal differencing learning algorithms that can lead to slower learning, really. But still, I think it's still a fact, a matter of fact, that deep reinforcement learning is still the best candidate we have at this point in time to develop highly sophisticated and capable control strategies for autonomous systems. There's now a more recent line of work that is based on foundation-based models inspired by LLMs, and now they've been made multimodal and in other directions, and we do this as well. And they have some really interesting properties, and they can do some really interesting things across the board. But if you really care about designing an algorithm that hardcore maximizes expected return as a mathematical quantity that we care about, then deep reinforcement learning is still the best candidate, I think, that we have, even though it can be quite slow in certain environments. And then you just have to be smart about how you set up the training, basically. By the way, I want to say one more thing I want to add to that is there's some other interesting complementary things that are happening. For example, another big factor that slows down deep reinforcement learning is the fact that we do our gradient computations in the GPUs, but the simulations run on the CPUs. So there's a lot of channeling latency going on when data is transitioned in the buffers between the CPU and the GPU. And that's why there's now new initiatives to actually develop frameworks where everything is moved into the GPU environment. So both the algorithm implementations and the environment implementations. This is called JAX. There's other versions, but JAX is developed by Google, and you can have JAX accelerated implementations where everything is executed as a series of matrix multiplications in the GPU environment. And then you get hundreds or thousands of times acceleration, which is really impressive. And in my group, we actually have a few project clusters. We are developing JAX accelerated environments for deep RL pipelines, and it becomes really fast if you do that. But it's not easy to do. It requires some complicated programming. Anyway, just to throw something in, I think that sort of gives hope for making it even faster and nicer to use, basically. Yeah. Yeah. So there's two JAX environments for multi-agent reinforcement learning. One is developed by one of our friends in Oxford, and one is developed by a team in South Africa in a company called InstaDeep, and that's called MAVA. And they already have an LBF implementation there from our lab. So they actually took a bunch of our environments from our lab and JAXified them, basically. So LBF is already there. And the guys in Oxford, I'm not sure if they have a JAX version of LBF. Maybe not.
This question is related to the field itself and the reinforcement learning field, whether it is a single agent or multi-agent. But it came to me from the last question about the downsides, like that reinforcement learning take a lot of times and episodes to converge. Because correct me if I'm wrong, but I'm always being taught that reinforcement learning kind of tries to mimic how we humans learn from, especially when we are very young, by trial and error from the environment. And what would you say is the current direction that the field is taking about, for example, we heard about like few shot learning or zero shot learning that tries to, reduce the amount of time or the amount of episodes that we learn. What would you say about that in the current, on the state of the art of the field?
So I think actually that also relates back to the online question that we had, and I think this could be interesting for a lot of students here, a lot of people here. So another big problem with deep reinforcement learning, I'm not sure if I would call it a problem, but how we've been doing it so far, is that we train it from scratch, absolutely from scratch for every task that we want to do. And that can be slow, right? If I have 100 tasks and I want to train 100 policies, it can be slow for every one of these. That's why there's a lot of attention now in research on this idea of generalization. We want to have policies and algorithms that can do very efficient transfer and generalization across tasks. so that if I understand to solve task A, B, C, then I can also solve the other tasks, in other environments, as long as they are related in some interesting way to these other tasks that I solved before. So there's a huge amount of research, including in our group and in other labs, where we try to develop algorithms that can learn policies that transfer very effectively across these different environments. And that, I think, is a huge deal because it makes the difference between a practical algorithm and a not practical algorithm. For example, if I have a policy that after long training can already do a certain task, the only way for me to do some other complex task that is related to this, if I have a limited budget, might only be to take that policy and tune it a little bit and then apply it here. But I might not have the budget to do the whole training again from scratch, right? It might just be too expensive. If you think about how much it costs to train in games like StarCraft 2, we're talking about millions of dollars, right? Really big money to train these kinds of models. And to do the transfer is a big deal. Then the transfer might be much, much cheaper because it might be much more computationally efficient to do that. So we try to create algorithms. And yesterday I was at Telefonica. They have a big lab by the seaside, and they do reinforcement learning research as well. I gave a talk about our research. And one paper that I like to introduce is this idea that we want to learn disentangled representations. I think that's a really cool idea that you may want to check out as well. The idea that if you have a reinforcement learning algorithm and you have a robot that sees a vision feed, a camera feed, the standard reinforcement learning algorithm is really slow in this space because it learns to correlate against the pixels that we get to see. But if these pixels change, then the policy fails. For example, if the colors change in the background or something like that, the policy will fail because it correlates against those pixels. So, for example, we developed new algorithms for the first time, and was published last year in a couple of conferences, where purely from this vision feed, the agent is able to understand the ground truth factors that exist in the environment. For example, that there's floor color, wall color, object shape, and so on. And then if we take the same policy and transition it into a different environment, where only some of these elements change, for example, now there's a different color or whatever, or a different shape of the body, everything else still remains well defined and the policy can continue to operate. And that's a really strong property in terms of achieving robustness. That we require for deep reinforcement learning to be practical and to be closer to how humans operate, because humans can do this sort of thing as well. So I just wanted to give you this one example as a line of research that tries to produce more efficient, more capable, more generalizable policies. We haven't talked about any of this stuff here, but there is this kind of research that tries to do this. And if you want to learn more about this particular idea of disentangled representations, you can just go to our group website, you go to the publications tab, and then you just search for disentangled or disentanglement or something like that, and you should be able to find some papers.